Every detail in this story comes from real scientific research and observation. There is a planet in our solar system that looks from a distance almost exactly like Earth. It is nearly the same size, nearly the same mass. It formed from the same cloud of gas and dust at roughly the same time, about 4.6 billion years ago. For the first few 100 million years of its existence, scientists now believe it may have had liquid water on its surface. Shallow oceans, a sky, a water cycle. It had everything. And then something went wrong. Tonight, we are going there, to a world where the atmosphere weighs as much as 900 meters of ocean pressing down on every surface, where the clouds are made of sulfuric acid, where the average surface temperature is 465 degrees Celsius, hot enough to melt lead, hot enough to melt zinc, hot enough to soften aluminum. Where the sun, if you could see it at all through the permanent orange overcast, rises in the west and sets in the east because this planet rotates backwards relative to almost everything else in the solar system, where a single day lasts longer than a year. This is Venus. And here is what makes Venus genuinely difficult to think about. It did not have to be this way. 3 billion years ago, perhaps 4, something that resembled an ocean may have covered a significant portion of this surface. The isotopic signature of what little water vapor remains in the Venusian atmosphere today carries a chemical fingerprint of that vanished water. The ratio of deuterium to hydrogen in Venus's atmosphere is approximately 150 times higher than it is on Earth. That number is not a coincidence. It is a record. It is what remains when an ocean slowly loses its hydrogen to space, leaving the heavier isotope behind. The water was here, and then the planet burned it away. The first spacecraft to attempt a landing on Venus was destroyed before it reached the surface. The second was crushed. The third transmitted for just 23 minutes before the heat and pressure overwhelmed its instruments, becoming the first human-made object to send data from the surface of another planet. The engineers who built these probes knew what they were sending them into. They reinforced the hulls, they lined the electronics with insulation. They gave the landers internal cooling systems designed to buy just enough time, not to survive, but to transmit something before the end. Later missions brought cameras. In 1975, Venera 9 transmitted the first photograph ever taken from the surface of another planet. The image showed a landscape of angular, broken rocks, sharp edges, no rounding from erosion, no evidence of the slow, patient work of water over millions of years. The rocks looked recently formed, or at least recently exposed, geologically young in a way that raised immediate questions about what could have resurfaced this entire world within the last few 100 million years. The answer, scientists now suspect, involves one of the most violent geological episodes in the history of any planet we have ever studied. There are mountains on Venus taller than anything on Earth, measured from the surrounding plains. There are volcanic features that have no clear analog anywhere else in the solar system. There is a continent-scale highland region called Aphrodite Terra, stretching roughly 10,000 kilometers across the equatorial zone, whose surface has been deformed by forces that are still not fully understood. And underneath all of it, below the crushing atmosphere, below the orange sky, below the sulfuric acid clouds that circle the planet at nearly 100 meters per second, there may still be active volcanoes. As recently as 2023, a scientist reanalyzing radar images from the Magellan spacecraft found direct evidence of a volcanic vent that had changed shape between two observations taken 8 months apart. The vent had grown, the lava had moved. Venus, it appears, is not geologically dead. It is still alive. Tonight, we are going to spend time with this planet, not the Venus of mythology, not the symbol of beauty and morning light, but the actual place, the physics of it, the chemistry of it, the history of it, the deep geological story of how a world that may once have held oceans became the most hostile surface environment in the solar system. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Everything in this episode is drawn from peer-reviewed research, spacecraft mission data, and current scientific understanding. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Venus is the second planet from the Sun, orbiting at an average distance of approximately 108.2 million kilometers, compared to Earth's 149.6 million kilometers. That difference, roughly 41 million kilometers, sounds significant. In the context of the solar system, it is not very much. Venus and Earth are neighbors, cosmically speaking, and they show it in their physical specifications. The diameter of Venus is 12,104 kilometers. Earth's diameter is 12,742 kilometers. The difference is less than 5%. The mass of Venus is approximately 81.5% of Earth's mass. The surface gravity on Venus is 90% of what it is here. If you were standing on the surface of Venus, ignoring for a moment the temperature, the pressure, and the atmospheric composition, you would feel almost exactly as heavy as you do right now. These similarities are why, for much of the early 20th century, Venus was imagined as a kind of tropical twin. The planet is perpetually cloud-covered, and for a long time no one knew what lay beneath those clouds. The imagination filled in what instruments could not yet reach. Some scientists speculated about dense jungle, others proposed global oceans. The cloud cover was thick and bright and completely opaque, and it kept its secrets for longer than almost any other object in the inner solar system. The secrets, when they finally came out, were not what anyone expected. Venus rotates on its axis extremely slowly. One full rotation, one Venusian day, takes 243 Earth days. Its orbital period, the length of one Venusian year, is 224.7 Earth days. This means that on Venus, a single day is longer than a single year. The planet completes its orbit around the Sun before it finishes rotating once on its own axis. And then there is the direction of that rotation. Almost every planet in the solar system rotates in the same direction, counterclockwise when viewed from above the solar system's north pole. This is the inherited angular momentum of the protoplanetary disk from which everything formed. Venus rotates in the opposite direction, clockwise, retrograde. The Sun rises in the west and sets in the east. No other large planet in the solar system does this, with the partial exception of Uranus, which rotates on its side. Why Venus rotates this way is still debated. The leading hypotheses involve either a massive impact early in the planet's history that literally reversed its spin, or a complex resonance between the planet's slow rotation, its dense atmosphere, and the gravitational influence of the Sun, a resonance that gradually slowed and eventually reversed the original rotation over billions of years. Both mechanisms are physically plausible. Neither has been definitively confirmed. What is certain is that the slow, retrograde rotation has significant consequences for the planet's climate. On Earth, rotation drives atmospheric circulation, generates the Coriolis effect, creates the banding of weather systems into latitudinal zones, and helps maintain the magnetic field through the movement of the liquid iron core. Venus, rotating so slowly, does not have a meaningful global magnetic field. Its magnetosphere is induced, created by the interaction of the solar wind with the upper atmosphere rather than by an internal dynamo. This means Venus has very little protection from solar radiation at the atmospheric level. That lack of protection, combined with the composition of the atmosphere, is part of what made the planet's evolution go so differently from Earth's. The Venusian atmosphere is composed of approximately 96.5% carbon dioxide and 3.5% nitrogen, with trace amounts of sulfur dioxide, water vapor, carbon monoxide, argon, and other gases. Carbon dioxide is a greenhouse gas. It absorbs infrared radiation and re-emits it, trapping heat in the lower atmosphere. Earth's atmosphere contains only about 0.04% carbon dioxide, and that fraction is already sufficient to raise global temperatures significantly compared to what they would be without it. Venus has 96.5%. The result is the most extreme greenhouse effect in the solar system. Sunlight enters the atmosphere, reaches the surface, is re-radiated as infrared heat, and cannot escape. The surface temperature stabilizes not at the equilibrium temperature that would result from solar input alone, which would be roughly minus 40 degrees Celsius, given how reflective the cloud cover is, but at 465 degrees Celsius. The greenhouse warming on Venus accounts for approximately 500 degrees of additional temperature. Nothing in our solar system comes close to this effect. This is not a gentle warming. This is a planet that has trapped its own heat so completely that the surface temperature varies by only a few degrees between the poles and the equator, and by only a few degrees between day and night. The side of Venus facing away from the Sun is just as hot as the side facing toward it. The thermal mass of the atmosphere and the efficiency of its heat trapping is so complete that darkness and distance from the Sun have become almost irrelevant to surface temperature. The surface of Venus receives less solar energy per square meter than Earth does because of the planet's highly reflective cloud cover. Venus reflects about 70% of the sunlight that hits it, a figure called albedo. Earth reflects roughly 30%. Venus, paradoxically, is one of the most reflective objects in the solar system, and yet its surface is far hotter than any other rocky planet. Albedo is not protection. Albedo only affects how much sunlight reaches the surface. Once the surface has absorbed what little does penetrate, the atmosphere's opacity to infrared radiation determines what happens to that energy. And on Venus, essentially none of it escapes. The atmosphere extends from the surface to a height of roughly 250 kilometers, though the most meteorologically active region lies between about 45 and 70 kilometers altitude. This is where the cloud layers are, a complex layered structure of sulfuric acid droplets, forming what looks, from orbit, like a continuous featureless blanket of pale yellowish white. The clouds are not water vapor, they are sulfur dioxide and water vapor that have chemically combined under the conditions of the upper atmosphere to form droplets of concentrated sulfuric acid ranging from 75 to 96% concentration by mass. Rain falls from these clouds. Droplets of sulfuric acid form in the upper cloud decks, grow large enough to fall, and descend toward the surface, but they never arrive. The lower atmosphere is hot enough, approximately 200 to 250 degrees Celsius, at an altitude of about 30 kilometers, that the droplets evaporate long before they reach the ground. This phenomenon is known as virga, precipitation that falls but evaporates before it touches the surface. It happens on Earth as well, but on Earth virga involves water. On Venus it involves sulfuric acid dissolving back into vapor somewhere over the roasting middle atmosphere. The surface itself then is in a kind of chemical isolation. The corrosive clouds stay aloft. The pressure holds everything down. The temperature keeps everything in a state of slow, permanent chemical equilibrium. And yet the surface is not static. The Magellan spacecraft, which mapped approximately 98% of Venus's surface between 1990 and 1994 using synthetic aperture radar, revealed a landscape of extraordinary geological diversity and violence. There are vast volcanic plains covering most of the lowland terrain, formed from enormous flows of low-viscosity basaltic lava. There are shield volcanoes, some of them enormous. There are features called coronae, circular structures formed when plumes of hot material from the mantle push up through the crust, causing it to flex, fracture, and partially collapse. And there are tesserae, regions of highly deformed, ancient-looking terrain that stand above the volcanic plains, like geological islands. The tesserae on Venus are considered the oldest surface material currently visible, and they preserve a record of crustal deformation that predates the most recent volcanic resurfacing event. What that record says, and how old the tesserae really are, is one of the central questions the next generation of Venus missions is designed to answer. The volcanic plains themselves tell a striking story. Crater counts on planetary surfaces are used to estimate age. The more craters, the older the surface, because older surfaces have had more time to accumulate impacts. Venus has a surprisingly low crater density. The current surface appears to be, on average, somewhere between 300 million and 700 million years old, young by planetary standards. On Venus, there are no tectonic plates in the Earth sense. There is no evidence of seafloor spreading, no subduction zones, no linear mountain chains formed by continental collision. Instead, scientists have proposed a model called episodic resurfacing, the idea that Venus periodically accumulates enough internal heat to trigger a catastrophic global volcanic event in which the entire lithosphere becomes unstable, partially melts, and is overrun by massive lava flows that pave over essentially everything. Then the planet cools, the lithosphere stiffens again, and the cycle begins anew. The last such event may have occurred somewhere between 300 and 700 million years ago. The next one, if the model is correct, has not yet happened. Venus is not finished. The planet is still geologically active, still chemically processing its surface and atmosphere, still radiating the deep heat of its formation and the ongoing decay of radioactive elements in its interior. It is a world in process, not a world in stasis. 3 new missions are currently planned or in development to address that question. They will arrive in the 2030s, and they will attempt to answer a question that has been shaping since the first isotopic measurements confirmed the existence of lost water. Was Venus once a planet where something could have lived? That question does not have a clean answer yet, but the fact that it can be asked at all, the fact that the chemistry, the physics, and the geometry of the early solar system leave room for the possibility, is remarkable. Venus is not just a cautionary tale about greenhouse warming, though it is that. It is also an alternate history. It is a version of Earth that was pushed in a different direction by small differences in orbital distance, solar luminosity, rotational dynamics, and geological timing that compounded over billions of years into the most extreme surface environment in the solar system. Everything that will follow in this story is drawn from that divergence. From the moment the sun grew slightly brighter and the water vapor in the Venusian atmosphere began to absorb just a little more heat than it radiated. From the moment the feedback loop engaged. From the moment a planet that might have been habitable began, slowly, and then not so slowly, to burn. The surface temperature right now, on the night side of Venus, in the deep lowland basaltic plains that cover most of the planet, is 465 degrees Celsius. It has been that temperature, more or less, for several 100 million years. And somewhere beneath that heat, there is a ghost, the isotopic memory of an ocean that may once have been. The temperature does not drop significantly at night. The dense atmosphere retains heat so efficiently that the day-night temperature difference at the surface is only about 10 degrees Celsius. The entire night side of Venus, a hemisphere that receives no direct sunlight, maintains a temperature that would melt most metals used in industrial manufacturing. The clouds above, meanwhile, move at entirely different speeds than anything at the surface. At cloud top altitude, approximately 65 to 70 kilometers above the surface, the atmosphere circulates at speeds of up to 100 meters per second, more than 360 kilometers per hour. This phenomenon is called atmospheric superrotation. The atmosphere at these altitudes completes a full circuit of the planet in approximately 4 Earth days, even though the planet itself takes 243 Earth days to rotate once. The cloud layer laps the surface more than 60 times for every single rotation of the solid planet below it. From the ground, looking up, the clouds would appear to move perceptibly across the sky, not like Earth clouds drifting on a gentle afternoon, but like a fast river of haze, orange-tinted and featureless, carrying its chemical cargo from horizon to horizon in hours rather than days. The light at the surface, on the day side, is roughly equivalent to an overcast day on Earth. Not darkness, the thick atmosphere scatters and diffuses enough sunlight to illuminate the surface to a level comparable to a heavily clouded afternoon, but the light would have a reddish-orange quality, filtered through those kilometers of absorbing gas and particulate cloud above. Orange everywhere. The rocks, the plains, the fractured highlands in the distance, all bathed in a dim, permanent, reddish twilight. And over all of this, silence. Not the comfortable silence of a cool night, not the empty silence of deep space. The surface of Venus would have a sound environment shaped by its dense atmosphere, but the absence of wind at the surface level, the absence of water, the absence of anything living or moving, would produce a stillness of a particular, almost suffocating quality. No rain touches the ground. No wave breaks on any shore. No animal moves through the volcanic plains. only the slow, planetary creaking of a world still working through its own geological processes, volcanic systems venting somewhere below, rocks slowly expanding and contracting through the minor temperature variations between day and night, the occasional distant tremor of a surface adjusting under its own weight. Venus is alive in the way that the deep interior of the Earth is alive, through heat and pressure and chemistry, through processes that operate on timescales of millions of years and leave their evidence in rock formations and atmospheric chemistry rather than in anything a human observer would notice in a single lifetime. But it is alive. It is still processing. And that process began, as all planetary stories begin, in the chaos of formation, in the swirling disk of gas and dust that surrounded the young sun approximately 4.6 billion years ago, when everything in the inner solar system was still being assembled from violence and collision and heat. What Venus was in those first hundreds of millions of years, and what it might have been if things had gone even slightly differently, that is the deeper story. And it begins with water. Water in the early solar system was not rare. It was everywhere. Ice-bearing planetesimals, small rocky and icy bodies, ranging from a few meters to a few kilometers across, formed throughout the outer regions of the protoplanetary disk and migrated inward through gravitational interactions with the gas giants. They collided with the forming terrestrial planets, delivering volatile compounds including water, carbon dioxide, nitrogen, and organic molecules. This delivery process, sometimes called the late veneer or late accretion, is thought to have been responsible for a significant fraction of Earth's water inventory, and by extension for Venus's as well. The two planets formed in similar regions, from similar materials, and were subjected to similar bombardment histories during the period of intense early solar system activity known as the Late Heavy Bombardment, which reached its peak approximately 3.9 billion years ago. If Earth received a significant water delivery from this process, Venus, orbiting in roughly the same neighborhood, almost certainly did too. The question is not whether Venus received water. The chemical evidence suggests it did. The question is how long it kept it. To understand what happened to Venus's water, it helps to understand the physics of a process called the runaway greenhouse effect. This is not the gradual century-scale warming that the term greenhouse effect evokes in contemporary discussions of Earth's climate. It is a fundamentally different phenomenon, a feedback loop with no natural stopping point, driven by the specific optical properties of water vapor under certain conditions of solar irradiance. The runaway greenhouse mechanism works like this. A planet with liquid surface water has a water cycle. Water evaporates from the surface, enters the atmosphere as vapor, rises, cools, condenses into clouds, and precipitates back to the surface. This cycle is stable because the amount of water vapor in the atmosphere at any given time is limited by temperature. Warmer air can hold more vapor, cooler air forces it to condense and fall. Under normal conditions, the atmosphere self-regulates. Warming causes more evaporation, which causes more cloud formation, which reflects some sunlight back to space, which provides some cooling. The cycle finds an equilibrium. But water vapor is also a greenhouse gas. A more powerful one, in fact, than carbon dioxide, though it operates differently. Water vapor absorbs infrared radiation across a broad range of wavelengths. At low concentrations, it contributes modestly to warming. But at high concentrations, in an atmosphere that has become hot enough for the entire ocean to begin evaporating significantly. Water vapor can absorb so much outgoing infrared radiation that the planet cannot cool itself, regardless of how much thermal energy it tries to radiate. This threshold is called the radiation limit, or the Simpson-Nakajima limit, after the researchers who formalized its mathematics. Once a planet crosses this threshold, once the solar irradiance is high enough, or the surface warm enough, for water vapor to saturate the atmosphere at concentrations above this critical value, the planet cannot achieve a stable temperature with liquid surface water. The ocean continues to evaporate. The temperature continues to rise. There is no equilibrium to reach. The system runs away. Venus may have crossed this threshold. The current scientific understanding, based on climate modeling work by researchers, including Michael Way and Anthony Del Genio at NASA's Goddard Institute for Space Studies, suggests that early Venus, during a period when the sun was approximately 70% as luminous as it is today, may have been able to maintain stable liquid water on its surface. Their modeling work found that under plausible early Venusian conditions, including a slower initial rotation rate, a shallow ocean, and cloud dynamics that differed from modern models, surface temperatures could have remained below the boiling point for as long as 2 to 3 billion years. 2 to 3 billion years. That is more time than it took for the first complex multicellular life to appear on Earth. If the modeling is correct, Venus was potentially habitable for a span of time comparable to the duration it took life on Earth to progress from simple prokaryotes to complex organisms. This does not mean life existed on Venus. It means that the physical conditions that are considered prerequisites for life, liquid water, a stable surface, moderate temperatures, may have been present for an extraordinarily long time on a planet that is now utterly incompatible with any biology we know of. What ended it was the sun. Stars brighten as they age. The sun today is approximately 30% more luminous than it was when the solar system formed. This gradual brightening, driven by the slow increase in the density of hydrogen fusion products in the solar core, which increases the core temperature and therefore the luminosity, has been occurring throughout the sun's lifetime and will continue until the sun eventually leaves the main sequence several billion years from now. For Earth, this gradual brightening has been largely compensated by long-term changes in the composition and dynamics of the atmosphere, particularly the drawdown of carbon dioxide through silicate weathering and the carbon cycle. Life itself has played a role in this compensation. The biological and geochemical processes that remove carbon from the atmosphere and lock it into limestone, organic matter, and other carbon sinks have helped keep Earth's surface temperature within a habitable range, even as the sun has grown steadily brighter. Venus had no such regulation, whether because it lacked the geological machinery for efficient carbon cycling, or because its water supply was insufficient to sustain a long-term silicate weathering sink, or because some other factor pushed it past the stability threshold before life could establish itself, Venus did not compensate. The sun grew brighter. The water vapor content of the atmosphere increased. The greenhouse warming increased. The temperature rose. More water evaporated. The greenhouse warming increased further. And once the feedback loop fully engaged, the outcome was inevitable. The ocean, if it existed, would have evaporated completely, not all at once, but over a geological timescale of perhaps tens to hundreds of millions of years. As the water vapor accumulated in the upper atmosphere, it was subjected to photodissociation, the process by which ultraviolet radiation from the sun splits water molecules into hydrogen and oxygen. The hydrogen, being light, escaped to space. The oxygen remained, and over time was absorbed into surface rocks through oxidation reactions. The water was gone, dissociated into its components, with the hydrogen lost to space and the oxygen locked into minerals. What remains of that water is the isotopic signal. The ratio of deuterium, heavy hydrogen with one neutron in the nucleus, to ordinary hydrogen in Venus's atmosphere is approximately 0.016, compared to approximately 0.00016 in Earth's ocean water. This is a factor of about 100, sometimes cited as 150 depending on measurement method. Deuterium is heavier than ordinary hydrogen. When hydrogen escapes to space through Jeans escape, the process by which individual atmospheric molecules with sufficient thermal velocity exceed the planet's escape speed and are lost, the lighter hydrogen atoms escape more easily than the heavier deuterium atoms. Over time, the escaping hydrogen is preferentially the ordinary light hydrogen. What remains behind is enriched in deuterium. The degree of enrichment in Venus's atmosphere tells scientists something about how much water was originally present and how completely it was processed out of the system. The enrichment is so extreme, so far beyond what any other process could plausibly produce, that water loss on a massive scale is the only explanation that fits. Venus lost an ocean, or something that functioned as one. The exact depth and extent of that ocean is unknown. Some models suggest it may have been equivalent in volume to Earth's current oceans, though spread more shallowly across the surface. Others suggest a shallower body, perhaps covering only portions of the lower elevation terrain. None of the data currently available can distinguish between these scenarios with confidence. But the fact of the water loss is not in question. Something was here, and it is gone. What remains, in the atmosphere, in the chemistry of the rocks, in the isotopic fingerprint of the hydrogen that did not escape, is a record of transformation, of a world that had water and warmth and the basic prerequisites for complexity, and then systematically dismantled itself, not through any single catastrophe, but through the slow, inexorable operation of physics over billions of years. Understanding this record is not merely an exercise in planetary nostalgia. It has direct implications for how we think about habitability elsewhere in the galaxy. Venus demonstrates that a planet can be located within what astronomers call the habitable zone, the range of orbital distances at which liquid water can theoretically exist on a rocky surface, and still fail to maintain habitability over geological time. It demonstrates that the inner edge of the habitable zone is not a sharp boundary, but a zone of uncertainty, where the specific history of a planet's formation, its initial water inventory, its rotational dynamics, and its geological evolution all interact to determine whether it stays habitable or tips into a runaway state. Earth sits just far enough from the sun, just barely far enough, that it has not crossed the Simpson-Nakajima threshold. Venus sits just close enough that as the sun brightened, it did. The margin between these outcomes is approximately 41 million kilometers of orbital distance. That is the difference between a planet with oceans and a planet with sulfuric acid clouds, between a world with weather and a world with a furnace, between a surface where liquid water has persisted for more than 4 billion years and a surface where lead exists as a liquid. The margin is not wide. Now consider what the surface of Venus must have looked like 3 billion years ago if the climate models are correct. This is where the science gives way, briefly, to imagination, informed imagination, grounded in what the models and the geological records suggest, but imagination nonetheless, because no spacecraft has ever photographed the early Venus. No instrument has ever sampled its ancient rocks. What follows is a reconstruction, a scientific inference rendered as seen. The light would have been different. 3 billion years ago, the sun was less luminous, the sky above early Venus. If an ocean existed and if the cloud dynamics behaved as the climate models suggest, might have been partially clear, perhaps not the blue sky of Earth, given the different atmospheric composition, but something less opaque than the permanent overcast of today. Light reaching the surface would have been stronger, more direct, less filtered. The surface itself would have been covered in the lowland regions with water, liquid water, moving slowly, accumulating in the basins between volcanic highlands. The chemistry of that water would have been different from Earth's oceans. The dissolved mineral content would have reflected the basaltic crust below, possibly more alkaline, possibly less saline, certainly different in ways that we do not yet know how to calculate. But it would have been liquid, it would have had a surface tension, it would have reflected light. The Tessera Highlands, the regions of ancient deformed terrain that survive today as the oldest exposed surface on Venus, would have been islands or continental margins or coastal highlands rising above the shallow seas. Their surfaces would have been exposed to weathering, to rain, to the slow chemical conversation between liquid water and rock that on Earth has been ongoing for more than 4 billion years. If that conversation was happening on Venus, if water was reacting with silicate rocks, drawing down carbon dioxide, locking carbon into carbonate minerals, then Venus may have had a functioning carbon cycle, a self-regulating mechanism, something that could, in principle, have compensated for some portion of the increasing solar luminosity. But it was not enough. Whether the carbon cycle was too slow, or the water too shallow, or the volcanic resupply of carbon dioxide too rapid, or some combination of all of these, the compensation eventually failed. The sun continued to brighten. The water vapor began to accumulate faster than it could be rained back out. The feedback loop engaged. What that transition looked like at the surface is beyond current scientific modeling to reconstruct in detail. It was probably not sudden. The ocean did not evaporate in a single catastrophic event. It drained gradually, over millions, perhaps tens of millions of years, as the atmosphere thickened, as the greenhouse warming intensified, as the rain that fell back to the surface became slightly less frequent, as the evaporation slightly outpaced the precipitation, year after year after year. The shorelines retreated. The shallow seas became shallower. The exposed rock, no longer covered by water, began to heat in the intensifying greenhouse. Rock that had been chemically locked by the cool, wet conditions of a functioning water cycle began to bake, releasing gases, more carbon dioxide, more sulfur dioxide, into the already thickening atmosphere. The feedback loop fed itself. And at some point, perhaps 2 billion years ago, perhaps 1.5 billion, the timing is genuinely uncertain, the last liquid water on the surface of Venus evaporated. The last rain that could reach the ground fell and immediately turned to vapor. The water cycle, which had been functioning for billions of years, ended. What remained was the atmosphere, thick with carbon dioxide that had accumulated over billions of years of volcanic outgassing, with no ocean and no silicate weathering to remove it, dense with sulfur dioxide from ongoing volcanic activity, which combined with the residual water vapor to form the sulfuric acid cloud layers that now define the planet's visible appearance. Hot, increasingly hot, as the greenhouse effect, freed from any compensating mechanism, drove the surface temperature upward to its current equilibrium. The transition from ocean world to furnace world did not happen overnight, but it happened, and it happened on a planet that in its early history may not have been very different from the one you are lying on right now. That parallel is worth sitting with. Venus is the same age as Earth. It formed from the same materials, in the same region of the same solar system, under the same young star. For perhaps a third of the age of the universe, it may have had liquid water, a functioning atmosphere, and surface conditions that were, if not hospitable by any standard we could tolerate today, at least within the range that liquid chemistry can operate. And then, over geological time, it transformed. Only the size is the same, only the mass, only the deep interior, still warm, still processing, still carrying the original heat of accretion and the ongoing energy of radioactive decay. Only that part of the planet is continuous with what it was at the beginning. Everything else has been remade. And the agent of that remaking, the single factor most responsible for the divergence of Venus from a potentially habitable world to the most hostile surface environment in the solar system, was not a collision, not a gamma-ray burst, not a passing rogue star. It was 41 million kilometers. The distance between Venus's orbit and Earth's orbit. In the scale of the solar system, in the scale of the galaxy, in the scale of the universe, that distance is almost nothing. And it made all the difference. Venus is not a dead world. It is a world in a different phase of its life, a phase that nothing in our experience of Earth prepared us to imagine until the spacecraft went there and the data came back and the numbers told a story that no one who first dreamed of a tropical Venus could have anticipated. The full story of that surface, what it looks like, what it is made of, what the instruments of the Veneeralanders saw before they failed, is where this journey continues. The surface has been waiting for a long time. Now let us go to it. The first human-made instruments to reach that surface did not survive long enough to understand it fully. They were not designed to. They were designed to reach it at all, to descend through 92 atmospheres of pressure, through temperatures that exceeded every material specification on record at the time, and to transmit something before they failed. What they transmitted changed the course of planetary science. In the 1960s, before any spacecraft had reached Venus, the dominant view of the planet among many scientists and essentially all of the public was shaped by inference and imagination. The cloud cover was too thick to see through. Spectroscopic measurements from Earth had revealed some of the atmospheric composition. Carbon dioxide had been detected as early as 1932, but the surface conditions were unknown. Models existed, but they ranged widely, and the uncertainties were large enough to accommodate almost any scenario. The Soviet space program in the mid-1960s decided to send spacecraft to find out. Venera 1 launched in February 1961 and lost contact with Earth 7 days after launch, becoming the first spacecraft to fly by Venus, though it could not transmit any data. Venera 2 flew by Venus in February 1966, again without transmitting useful data. Venera 3 that same month became the first spacecraft to reach the surface of another planet, but the communications system failed before any data could be returned. 3 attempts, 3 failures to receive data. The engineering teams went back to their calculations. The problem was not the spacecraft design in a general sense. It was that the actual conditions on Venus, the pressure, the temperature, the corrosive chemistry of the atmosphere, were so far beyond what anyone had confidently modeled that the vehicles were simply not built to survive them. When they entered the actual Venusian atmosphere and began encountering real conditions, they failed. So the engineers redesigned. Venera 4, launched in June 1967, was the first spacecraft to successfully return atmospheric data from Venus during its descent. It measured temperatures up to 262 degrees Celsius and pressures up to 22 atmospheres before it stopped transmitting, at an altitude still far above the surface. The probe had been crushed before it reached the ground. But it had returned data. It had confirmed that the atmosphere was primarily carbon dioxide. It had demonstrated that the conditions were survivable for at least part of the descent. Venera 5 and 6, in 1969, returned additional atmospheric data, but also failed before reaching the surface. Venera 7 in 1970 was different. It had been reinforced to withstand pressures up to 180 atmospheres, nearly double the actual surface pressure, providing a significant safety margin. It entered the atmosphere on December 15, 1970. It descended, and it reached the surface. It transmitted for 23 minutes. The data it sent included a surface temperature of approximately 465 degrees Celsius and a pressure of approximately 90 atmospheres. The transmission was weak. The lander had apparently rolled or fallen to one side upon impact, partially blocking the antenna. Mikhail Marov, a Soviet scientist, later analyzed the raw signal and found that even the apparently dead period after the main transmission contained a faint carrier wave. The lander had been transmitting the whole time. The antenna angle was just bad enough that only a fraction of the signal reached Earth. 23 minutes on the surface of Venus. That was the sum total of direct surface observation, temperature, pressure, orientation, before the heat overwhelmed the instruments and the signal went silent. But it was enough to confirm what the atmospheric measurements had been converging on. Venus was not tropical. Venus was not ocean-covered. Venus was a furnace. And the engineers and scientists who had been working on these missions, who had watched probe after probe fail or return partial data, who had been incrementally closing in on the truth for nearly a decade, they now knew. The planet was real, the numbers were real, and the next challenge was not just to survive the surface for a few minutes, but to see it. That challenge, building a spacecraft that could not only land and transmit data, but actually open a camera shutter and photograph the landscape of another world in an environment that destroyed everything, would take 5 more years to solve. And when it was solved, what the cameras showed was unlike anything the optimists had hoped for, and unlike anything the pessimists had feared, because nobody had imagined it correctly. The rocks were sharp, not rounded by water, not smoothed by wind-driven sand over millions of years. Sharp, angular, fractured, as if they had been broken recently, or at least in a geological sense recently, and had not spent enough time in any erosive environment to lose their edges. A landscape without the patient work of water. A surface that told its history in the absence of something, rather than in its presence. And that absence, that geological silence where water's effects should have been, was perhaps the most eloquent data point the cameras returned. The ocean was gone, the evidence of its absence was everywhere, and the planet had moved on, as planets do, into whatever it was becoming next. The surface was waiting to be understood. It still is. And the machines we are building now, the ones that will follow the Venera landers by half a century, armed with instruments those Soviet engineers could not have imagined, are being designed to go back, to stay longer, to look more carefully, to ask the surface what it remembers. The Venera 9 lander touched down on October 22nd, 1975, on a slope in the Beta Regio region of Venus, a highland area near the equator, elevated above the surrounding volcanic plains by several kilometers. The descent had taken approximately 1 hour from atmospheric entry to surface contact, the parachute phase in the upper atmosphere, the aerodynamic braking in the middle atmosphere, the final powered descent through the lower kilometers, all of it had worked. The lander was intact, the instruments were functioning, and the camera system, which the engineering team had spent years designing to survive long enough to open its lens covers and capture an image, was ready. It had a window of approximately 53 minutes before the heat would overwhelm the cooling system. The lens covers opened. What the camera saw and transmitted back to Earth across the 88 million kilometers of space that separated Venus from Earth at that moment was a field of angular, broken rock, slabs, fragments, edges that caught the dim, diffuse light from above and threw it back with a clarity that surprised everyone who saw the image. The rocks were not rounded, they were not buried under deep dust or smoothed by the passage of wind over geological time. They looked, as one scientist later described, like a recently quarried surface, a landscape where something had broken the rock apart and the broken pieces had not yet had time to be worn down. No water had touched them, not recently, perhaps not for hundreds of millions of years, if the water ever reached this particular highland region at all. Venera 10, which landed 4 days later at a different site, returned a similar image, a different arrangement of rocks, a slightly different surface texture, but the same essential character: angular, sharp, geologically young-looking, in a way that raised immediate questions about the timescale of surface processes on Venus. These two photographs fundamentally changed how scientists thought about Venus. The planet was not covered in soft sediment. It was not a gentle, ancient world worn smooth by billions of years of slow erosion. It was a place where the surface was being actively shaped by processes that removed old material and replaced it with new. The question was what those processes were and how recently they had last operated. The answer, as subsequent missions would reveal, was volcanic. Massively, globally, repeatedly volcanic. The Magellan spacecraft, launched in May 1989 and arriving at Venus in August 1990, spent 4 years using synthetic aperture radar to map the planet's surface with a resolution of approximately 100 to 300 meters. Because Venus's surface is permanently hidden from optical observation by its cloud cover, radar was the only tool that could provide global topographic and surface texture data. Magellan's radar bounced microwave pulses off the surface and measured the return signal, building up a detailed map of surface roughness, elevation, and reflectivity across essentially the entire planet. What it found was a geologically complex world, unlike any other. The surface of Venus, as mapped by Magellan, can be broadly divided into three types of terrain. Lowland volcanic plains cover approximately 80% of the surface. These are vast, relatively flat regions of basaltic lava, dark, dense, fine-grained rock that forms when low-viscosity magma erupts at the surface and flows across large areas before cooling and solidifying. The Venusian plains are similar in composition to the ocean floors of Earth, which are also basaltic, though the volcanic processes that created them operated in the complete absence of water. Highland regions, the tesserae and major elevated areas, cover approximately 10% of the surface. These are the most geologically complex and least understood parts of Venus. Tessera terrain, in particular, is characterized by intersecting ridges and troughs that cross each other at multiple angles, creating a crumpled, corrugated surface texture that is visible in radar imagery as a distinctive crosshatched pattern. The tesserae are considered the oldest terrain on Venus, predating the most recent volcanic resurfacing event. They are the primary target of the Da Vinci mission's atmospheric probe, which will descend toward the Alpha Regio Tessera highland. The third terrain type consists of volcanic constructs, individual volcanoes, volcanic fields, and associated lava flows that rise above the surrounding plains. Venus has more volcanoes than any other planet in the solar system, with estimates ranging from tens of thousands to more than 1 million individual volcanic features, depending on the size threshold used for counting. Mont Mons, in the eastern Aphrodite Terra region, is the tallest volcano on Venus. Its summit rises approximately 8 kilometers above the mean planetary radius, the equivalent of sea level on a planet without seas. Its base is roughly 400 kilometers across. The total volume of volcanic material in the Mont Mons construct is comparable to some of the largest volcanic edifices on Earth, though the specific history of its eruption record is not yet known. Sapus Mons, another large shield volcano, rises about 4 kilometers and has a distinctive double summit structure visible in Magellan radar imagery. The flanks of both volcanoes show extensive lava flow channels, elongated features formed when lava tubes or surface channels carried magma away from the summit and down the flanks, leaving behind the solidified walls of the conduit after the lava drained. These channels can extend hundreds of kilometers from the source volcanoes, crossing the surrounding plains, and sometimes showing evidence of multiple flow episodes from different eruption events. The longest volcanic channel system on Venus and in the entire solar system is called Baltus Vallis. It extends approximately 6,800 kilometers across the surface, longer than the distance from New York to Los Angeles and back again. Baltus Vallis is not a river valley. It is a lava channel, a conduit carved by flowing magma, either mechanically by the erosive force of the flowing rock, or thermally by the heat of the lava melting and assimilating the substrate below. Its length implies either a single catastrophic eruption of extraordinary volume, or a sustained period of volcanic activity that kept the channel active for an extended time. Both scenarios are geologically remarkable. Alongside the large volcanic constructs, Magellan identified coronae, circular or oval structures formed by mantle plumes. When a column of hot material rises from the deep interior and pushes against the underside of the lithosphere, the overlying crust domes upward, fractures radially, and may eventually partially collapse back down as the plume cools or migrates. What remains is a circular depression surrounded by a ring of fractured terrain with radial and concentric fracture systems and associated volcanic flows spreading outward from the structure. More than 500 coronae have been identified on Venus. They range in diameter from approximately 60 kilometers to over 2,600 kilometers. The largest, Artemis corona in the southern hemisphere, has a diameter of approximately 2,600 kilometers and is surrounded by a raised ring of ridges and a complex system of interior deformation that records the history of the plume event that created it. On Earth, mantle plumes produce features like Hawaii and Iceland, volcanic island chains, or isolated hotspot volcanoes. The plumes exist on Earth too, but their effects are modified by the movement of the overlying tectonic plates, which carry the surface away from the plume and create chains of volcanic islands rather than large stationary corona structures. Venus does not have mobile plates in the same sense. The crust appears to be largely stationary relative to the underlying mantle, so plumes punch through the lithosphere in the same location over extended periods, building up the distinctive corona architecture rather than leaving a trail of extinct volcanic islands behind. This difference, mobile plates on Earth, largely static crust on Venus, is one of the most fundamental distinctions between the two planets, and its causes are still debated. On Earth, plate tectonics is driven by the convection of the mantle. Hot material rises, spreads, cools, and sinks back down, dragging the rigid plates at the surface with it. The process is lubricated, in part by water. Water lowers the melting point of rock and reduces the viscosity of the mantle, making convection more vigorous and the plates more mobile. It also weakens the rock at plate boundaries, making subduction, the process by which one plate slides beneath another, mechanically feasible. Venus has essentially no water. Its mantle is dry in the planetary science sense. The absence of water is thought to have made the Venusian lithosphere stiffer and more resistant to the initiation of subduction. Without subduction, the plate tectonic cycle cannot establish itself, because subduction is what drives the surface plates, recycling old oceanic crust back into the mantle and pulling the new crust at spreading centers along behind it. Without that recycling mechanism, the crust thickens and stiffens over time, becoming increasingly resistant to the forces that drive plate motion. The result is a planet where heat builds up in the interior because it cannot escape through the efficient, continuous recycling of plate tectonics. On Earth, the mantle loses heat steadily and continuously through the process of seafloor spreading. On Venus, the heat cannot escape this way. It accumulates in the interior until the lithosphere, heated from below, becomes unstable and partially melts. Then it releases catastrophically in the kind of global volcanic resurfacing event that the crater count data and surface age estimates suggest has happened at least once in the last billion years, and possibly multiple times. This mechanism, called the stagnant lid convection regime with episodic overturning, is the leading model for how Venus manages its internal heat budget, It predicts a planet that appears geologically quiet for extended periods and then undergoes dramatic global-scale volcanic episodes. The timing and frequency of these episodes is controlled by the rate of heat accumulation and the mechanical properties of the lithosphere, both of which depend on the planet's interior temperature, composition, and the presence or absence of water. The current surface of Venus is consistent with a resurfacing event that concluded somewhere between 300 million and 700 million years ago. Since then, the planet has been in a post-resurfacing phase, with ongoing but more localized volcanic activity rather than a global catastrophic event. The 2023 Herrick and Hensley study, published in the journal Science, provided the first direct observational evidence of contemporary volcanic activity on Venus by comparing two Magellan radar images of the same region, taken 8 months apart in 1991. In one image, a volcanic vent on the flank of Mont Mons appeared as a roughly circular feature approximately 2 kilometers across. In the second image, the same vent had changed shape and appeared larger, with a different surface texture. The change was consistent with a volcanic eruption that had partially filled the vent with new material, expanding its floor and altering its walls. This is not dramatic by Earth standards, where volcanoes erupt continuously and visibly, but on Venus, where the surface was last directly observed by spacecraft in the early 1990s, finding direct evidence of change within a single mission's dataset was significant. It confirmed what the atmospheric chemistry, particularly the unexpectedly high concentrations of sulfur dioxide detected in some altitude ranges, had been suggesting. Venus is still erupting. The volcanoes are still working. The planet is still releasing its internal heat through the only mechanism available to it, given the absence of plate tectonics, localized volcanic venting, building and rebuilding the surface, one eruption at a time, waiting for the next global crisis that will remake everything again. And among the differences between Venus and Earth, the absence of water stands as the most consequential. Water changed everything on Earth. It lubricated the plates. It weathered the rocks. It built the carbon cycle. It enabled life, and life in turn modified the carbon cycle. And the combination of those two processes kept the planet within a habitable range, even as the sun grew slowly brighter over 4 billion years. Venus had water too once, and then it didn't. The geology that Magellan mapped is the geology of what came after, the geology of a world that had already crossed its threshold, already lost its ocean, already committed to the trajectory that led from whatever it was 3 billion years ago to what it is today. Every corona, every lava channel, every fractured tessera highland is a piece of a story that began with water and ended without it. The next part of that story involves looking more carefully at what the atmosphere is doing right now, not just its composition or its temperature, but its dynamics, its chemistry, its movement, and the strange and still unexplained phenomena that continue to puzzle the scientists who study it. Because the atmosphere of Venus is not a static thing. It is moving. It has always been moving. To understand why the atmosphere of Venus behaves as it does, it helps to understand its vertical structure, the way temperature, pressure, and composition change with altitude, and how those gradients drive the circulation patterns that make the Venusian atmosphere one of the most dynamically complex in the solar system. At the surface, the pressure is approximately 92 times that of Earth's atmosphere at sea level, and the temperature is approximately 465 degrees Celsius. Carbon dioxide at these pressures and temperatures is in a state called supercritical, above the critical point where separate gas and liquid phases can coexist. The atmosphere near the surface behaves more like a dense fluid than a conventional gas. It flows, but it does so slowly and with enormous thermal inertia. Small pressure differences produce very small wind speeds. Surface winds on Venus are typically 0.5 to 3 meters per second, a gentle breeze by Earth standards, but in the dense supercritical-like atmosphere, even a slow wind carries a substantial momentum flux. Moving upward from the surface, temperature decreases with altitude at a rate determined by the atmospheric lapse rate. The Venusian lapse rate in the lowest 30 kilometers of the atmosphere is approximately 10 degrees Celsius per kilometer, similar to Earth's dry adiabatic lapse rate. This means that at an altitude of 30 kilometers, the temperature is roughly 170 degrees Celsius, still far above Earth's boiling point, but dramatically cooler than the surface. Between approximately 45 and 65 kilometers altitude lies the main cloud deck of Venus. This is the region where sulfuric acid droplets form and accumulate, creating the permanent opaque cloud cover that gives the planet its characteristic appearance from space. The cloud layers are not uniform. Observations by the Venus Express spacecraft, which orbited Venus from 2006 to 2014, revealed a structured system of cloud layers with distinct optical and chemical properties. The lower cloud layer, between about 47 and 52 kilometers, consists of larger sulfuric acid droplets. The middle layer, from roughly 52 to 57 kilometers, contains smaller droplets. The upper cloud layer, from about 57 to 70 kilometers, is the most visible from space. It is the bright, featureless surface that reflects 70% of incoming sunlight back into space. Above the main cloud deck, from roughly 70 to 100 kilometers, is the mesosphere, a region of sharply decreasing temperature where the chemistry of the atmosphere transitions from the sulfur-dominated chemistry of the lower atmosphere to the more complex photochemical environment of the upper atmosphere. The temperature in the mesosphere drops to approximately -100 degrees Celsius at around 90 to 100 kilometers altitude. This extreme temperature inversion from 465 degrees at the surface to -100 degrees at 90 kilometers, a swing of more than 565 degrees Celsius over a vertical distance of 90 kilometers, drives powerful atmospheric dynamics that are still not fully characterized. The superrotation of the upper atmosphere is the most dramatic expression of those dynamics. At cloud top altitude, the atmosphere completes a full circuit of the planet approximately every 4 Earth days, compared to the 243 days required for the planet itself to rotate once. This means the atmosphere at these altitudes is moving roughly 60 times faster than the surface beneath it. The differential velocity between the fast-moving upper atmosphere and the slow-moving surface creates wind shear, a change in wind speed with altitude that should, in principle, be unstable and difficult to maintain. And yet it maintains itself. The Venus Express mission, using ultraviolet imaging to track the movement of cloud features, confirmed and refined earlier measurements of the superrotation speed and showed that it varies with latitude. Near the equator, the superrotation speed is highest, approximately 100 meters per second. At higher latitudes, the speed decreases and the circulation becomes more complex. At the poles, the Venus Express observations revealed polar vortices, large-scale cyclonic circulation features, analogous in some ways to the polar vortices that form in Earth's stratosphere in winter, but more persistent and more complex in structure. The southern polar vortex of Venus, in particular, attracted significant attention. Early observations showed it to be a double vortex structure, two rotating centers of atmospheric circulation, rather than a single one, with the pair slowly rotating around each other. Subsequent observations showed the vortex to be highly variable, changing shape and size over days to weeks. At times, it appeared as a single large cyclone. At other times, it fragmented into multiple smaller structures. The dynamics driving this variability are connected to the overall superrotation and to the heat distribution between the day and night hemispheres. The day-night thermal contrast in the upper atmosphere is much larger than at the surface. The day side of the upper atmosphere receives direct solar radiation and is significantly warmer than the night side. This contrast drives a planetary scale atmospheric wave pattern called a thermal tide, in which the atmosphere flows away from the heated day side and toward the cooler night side at some altitudes, and in the reverse direction at others. These thermal tides are thought to play a crucial role in maintaining the superrotation. They transfer angular momentum from the sun to the atmosphere in a way that keeps the cloud-level winds accelerated against the frictional forces that would otherwise slow them down. The exact mechanism involves a resonance between the tidal forcing and the natural oscillation modes of the atmosphere, and it has been the subject of detailed modeling work for decades. Venus Express also detected gravity waves in the atmosphere, waves produced when air parcels are displaced vertically from their equilibrium position and oscillate up and down under the restoring force of buoyancy. These waves propagate upward through the atmosphere and deposit their energy at higher altitudes, contributing to the complex momentum budget of the super-rotating cloud layer. What the combined picture of Venusian atmospheric dynamics reveals is a system of extraordinary complexity, driven by solar radiation, modified by the planet's slow rotation, shaped by the chemical and optical properties of the cloud layers, and expressing itself through the superrotation, the polar vortices, the thermal tides, and the gravity waves that move through it continuously. The atmosphere that exists now, thick with carbon dioxide, laden with sulfuric acid clouds, super-rotating at the top and nearly still at the bottom, is the accumulated result of billions of years of volcanic outgassing, water loss, photochemistry, and greenhouse warming. Every molecule in it is there for a reason. Every circulation pattern is the response of a physical system to the boundary conditions set by that long evolution. To study the atmosphere of Venus is, in a real sense, to read the memory of the planet. Not the whole memory. Much of it has been destroyed by the very processes that created the current state, but what remains is legible. If the instruments are sensitive enough and the measurements precise enough. That is what the next generation of missions is being designed to do. And those missions, and what they hope to find, are part of a story that extends beyond geology and atmospheric science into one of the most profound questions in planetary research: whether Venus, in its cloud layers, might still harbor something unexpected. Something that has found a way to persist high above the heat and pressure of the surface, in the only zone on the planet where temperatures and pressures fall within ranges that Earth biology can tolerate. That question is not yet answered, but it is being asked with increasing seriousness. The planet keeps its secrets in motion, always moving, always circling, never stopping. And somewhere in that motion, there may be an answer that changes how we think about life in the solar system. In September 2020, a team of astronomers led by Jane Greaves at Cardiff University published a paper in the journal Nature Astronomy reporting the detection of phosphine in the atmosphere of Venus. Phosphine is a molecule consisting of one phosphorus atom bonded to three hydrogen atoms, chemical formula pH3. On Earth, it is produced in two primary ways: industrially, in chemical manufacturing processes, and biologically, by anaerobic microorganisms, bacteria and archaea that live in environments without oxygen, such as the interiors of marshes, the guts of certain animals, and the oxygen-depleted layers of ocean sediment. Phosphine is not stable in an oxygen-rich atmosphere. It is rapidly oxidized, broken down by reaction with oxygen-containing compounds, and must be continuously produced to maintain any detectable atmospheric concentration. On Earth, the presence of phosphine in a particular environment is therefore considered a biosignature, a chemical signal associated with living processes. It is not proof of life on its own, because industrial production also generates it. But in a natural environment where no industrial chemistry is occurring, its presence implies biological activity. In the atmosphere of Venus, no industrial chemistry is occurring. The Greaves team reported a phosphine concentration of approximately 20 parts per billion in the Venusian cloud layers at an altitude of roughly 53 to 60 kilometers, a region where temperatures range from approximately 30 to 80 degrees Celsius, and pressures range from approximately 0.4 to 1 atmosphere. These are notably conditions within the range that some microorganisms on Earth can tolerate. The temperature and pressure at these altitudes on Venus are the closest to Earth-like conditions that exist anywhere on the planet. The phosphine detection, if real, required an explanation. Volcanic outgassing was considered. Some volcanoes on Earth produce trace amounts of phosphine, but modeling showed that Venusian volcanic chemistry could not produce phosphine at the observed concentrations without invoking eruption rates far larger than anything consistent with the observational evidence. Lightning-driven chemistry was also considered. Lightning in the Venusian atmosphere could drive high-energy chemical reactions that produce unusual molecules, but the same modeling issue applied. The concentration was too high for abiotic lightning chemistry to plausibly account for. The most parsimonious explanation, the research team argued, was biological production by microorganisms living in the cloud layer, organisms that had perhaps survived since an earlier era of the planet's history, when conditions were more hospitable near the surface, gradually retreating upward as the surface became uninhabitable, and finding a persistent niche in the cloud deck where liquid droplets, chemical energy sources, and tolerable physical conditions provided the minimum requirements for metabolic activity. The reaction from the planetary science community was immediate and divided. Other researchers were more skeptical. A reanalysis of the original spectroscopic data by other teams suggested that the phosphine signal might have been overestimated due to data processing choices, and that a revised concentration, accounting for calibration uncertainties in the ALMA radio telescope observations, was significantly lower, perhaps as low as 1 part per billion or less, rather than 20. At those concentrations, abiotic chemical processes could not be ruled out as efficiently. The debate has not been fully resolved. Subsequent observations with different instruments have returned inconsistent results, some finding a phosphine signal, others finding none or a much smaller one. The variability of the signal, if it is real, might itself be meaningful. Concentrations that change over time could reflect biological activity that varies with seasons or atmospheric circulation patterns, or they could simply reflect the noise floor of difficult remote observations of a faint spectral feature in a complex atmospheric background. What the phosphine controversy did, regardless of its ultimate resolution, was force the planetary science community to take seriously a question that had previously been considered more speculative than scientific. Could there be life in the clouds of Venus? The question has a history. Carl Sagan and Harold Morowitz raised it in a 1967 paper that considered the possibility of aerial biospheres on Venus and Jupiter. At that time, the surface conditions of Venus were just being established by the Venera program, and the cloud layer, with its relatively moderate temperature and pressure at certain altitudes, seemed to Sagan and Morowitz at least worth examining as a potential habitat. They proposed that photosynthetic organisms floating in the cloud layer, if they could manage the sulfuric acid chemistry and the ultraviolet radiation environment, might in principle derive energy from sunlight and sustain a metabolic cycle. The proposal was speculative. Sagan and Morowitz were careful to frame it as a possibility worth considering rather than a prediction, and for decades it remained in the category of interesting but unverifiable speculation, because no mission to Venus was capable of directly sampling the cloud layer chemistry at the level of detail needed to address the question. The phosphine controversy changed that calculus. Suddenly, there was, tentatively, controversially, subject to significant uncertainty, a potential chemical anomaly in the Venus cloud layer that existing abiotic chemistry could not easily explain. Not a confirmed biosignature, not proof of anything, but an anomaly, a data point that demanded an explanation. The Da Vinci mission, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is scheduled to launch in the late 2020s and will send a spherical atmospheric probe into the Venusian atmosphere. Among its instruments are mass spectrometers, capable of detecting trace gas concentrations at parts per trillion sensitivity, far more sensitive than the remote spectroscopic observations that produced the phosphine detection. Da Vinci will not definitively answer the question of life. It is not designed as an astrobiology mission, but it will provide atmospheric chemistry data of unprecedented precision, and that data will either support or rule out many of the proposed abiotic explanations for the phosphine anomaly. The Envision mission, led by the European Space Agency and currently planned for launch in the early 2030s, will orbit Venus and conduct a comprehensive, multi-instrument study of the planet's surface and atmosphere. Its instrument suite includes spectrometers capable of characterizing the cloud layer chemistry from orbit with higher resolution than previous missions. The Veritas mission, Venus Emissivity, Radioscience, INSAR, Topography and Spectroscopy, was approved by NASA and is being developed to provide the most detailed global surface map of Venus ever made, with radar resolution several times better than Magellan's, and with infrared spectroscopy capable of mapping the mineralogy of the surface. Together, these three missions represent a coordinated return to Venus after 3 decades of near neglect. The last dedicated Venus mission, Venus Express, ended in 2014 when the spacecraft exhausted its propellant and fell into the atmosphere. In the years since, Venus science has been largely dependent on reanalysis of old data and remote observations from Earth-based telescopes. The new missions will change that. Now consider what that cloud layer actually looks like, physically. At 55 kilometers altitude, the atmosphere of Venus has a pressure of approximately 0.5 bars, roughly half of Earth's sea level atmospheric pressure, comparable to what you would experience at the summit of a modest mountain. The temperature is approximately 27 degrees Celsius, warm but not lethally so. The sulfuric acid droplets that make up the clouds at this altitude are small, typically less than a micrometer in diameter, and dispersed at a concentration that makes the cloud layer more analogous to a dense haze than to the thick fog it might suggest from a distance. The visibility inside the cloud would be limited, perhaps a few hundred meters at most, depending on the local droplet concentration, but it would not be complete opacity. Light filters through from above, diffused and scattered by the cloud particles, arriving from all directions rather than from a single solar direction. The chemical environment at this altitude is hostile by Earth standards. Sulfuric acid at concentrations of 75 to 85% by mass is strongly corrosive to most biological molecules. It denatures proteins. It attacks lipid membranes. It reacts with nucleic acids. Any organism that attempted to survive in these droplets would need biochemistry fundamentally different from anything found in Earth life, not just tolerant of sulfuric acid in the way that acidophilic bacteria on Earth are tolerant of dilute acids, but actually operating in concentrated sulfuric acid as a solvent, using molecules that remain stable under these conditions. Whether such biochemistry is possible in principle is genuinely unknown. No laboratory experiment has ever demonstrated metabolic processes in concentrated sulfuric acid. No known organism uses it as a solvent. But the history of life on Earth is full of environments that were once considered too extreme for biology, and which turned out to harbor organisms that had evolved specific adaptations to exploit them. Hydrothermal vent communities, organisms living in highly acidic mine drainage, microbes in Antarctic ice, bacteria surviving in the intense radiation environments of nuclear reactors. The extrapolation from these Earth extremophiles to hypothetical Venusian cloud organisms is a long one, but it is not infinite. Sarah Seeger, a planetary scientist at MIT with a long history of work on biosignatures in exoplanet atmospheres, proposed a life cycle for hypothetical Venusian cloud organisms in detail. Her model was built around a specific observation about the physics of the cloud layer. The sulfuric acid droplets at habitable altitudes have a residence time in the atmosphere. They form, grow, fall, evaporate, and reform on a cycle driven by atmospheric circulation. A microorganism living inside a droplet would eventually be carried downward as the droplet fell under gravity into the lower atmosphere where temperatures and pressures quickly exceed anything biology can survive. The proposed solution was dormancy, an organism that could produce a desiccation-resistant spore, a dormant form analogous to the endospores produced by bacteria like bacillus on Earth, could survive the transit through the hostile lower atmosphere as a dry particle be lofted back upward by convective currents, encounter a new cloud droplet at the appropriate altitude, rehydrate, and resume active metabolism. This cycle, active in the clouds, dormant in the lower atmosphere, lofted back up, reactivated, could in principle sustain an aerial biosphere indefinitely, using the atmospheric circulation as a kind of conveyor belt that continuously refreshes the supply of organisms at the habitable altitude. The energy source for metabolism in this scenario would most likely be solar radiation, photosynthesis, using some wavelength of light that penetrates the sulfuric acid clouds and drives a chemical reaction in sulfur chemistry rather than in the oxygen, water, carbon dioxide chemistry of Earth photosynthesis, is one possibility. Chemosynthesis, deriving energy from the chemical reactions between sulfur compounds at different oxidation states, or between hydrogen and sulfur dioxide, which both exist in the Venusian atmosphere, is another. None of this is known, none of it has been measured. The discussion remains in the realm of theoretical biology and chemical plausibility assessment. But it is not arbitrary speculation. It is grounded in the specific physical and chemical conditions of a real environment that has been measured by real spacecraft, and it is informed by real understanding of the range of environments that life has been found to inhabit on Earth. The phosphine detection, if it holds up under further scrutiny, would be the first observational data point suggesting that something in the Venusian cloud layer is producing a molecule that existing abiotic chemistry cannot easily explain. It would not confirm life. It would simply place the question in a different category, from purely theoretical to empirically motivated. That distinction matters in science. Theoretical possibilities are considered and set aside with relative ease. Empirical anomalies require explanation. They demand data, they motivate missions, and missions produce data that either resolve the anomaly or deepen it. Venus, in this context, is not just a planetary science problem. It is a key reference point in the broader effort to understand where life can exist in the universe, not because it is likely to harbor life, but because it occupies a position on the boundary between possibly habitable and definitely not, and studying that boundary in detail is exactly the kind of work that makes the boundary legible. The planet that was once imagined as a tropical world, then revealed as a furnace, and then proposed as a possible habitat for aerial microbes. Venus has been many things in the scientific imagination, and it will likely continue to surprise as the next generation of missions brings new data. What it has always been, underneath all of those revisions, is a mirror. Not a flattering one, not one that shows Earth as it is, but one that shows Earth as it might have been, or as it might yet become, if the conditions that distinguish the two planets were slightly different. And at 465 degrees Celsius, surrounded by sulfuric acid clouds, turning backwards on its axis in an orbit just 41 million kilometers closer to the Sun than ours, Venus holds that image up patiently in the perpetual orange twilight of its surface, waiting for the instruments sophisticated enough to read it fully. The machines are being built. The questions are ready. And the planet is not going anywhere. In the cloud layers above the furnace, at the altitude where the temperature and pressure are briefly, tantalizingly close to what you would find on a warm afternoon on Earth, something is circling, something is moving. Whether that something is merely chemistry or something more is a question that the next decade of planetary exploration is specifically designed to answer. The silence of that altitude, 55 kilometers above the molten lead plains, above the crushing pressure, above the still and super-hot lower atmosphere, is not empty. It is full of chemistry. It is full of motion. And it may be full of something else entirely. The answer is coming. It is riding on the instruments of missions currently in development, on the calculations of scientists who have dedicated their careers to understanding why Venus became what it is, on the slow and patient work of building spacecraft capable of surviving long enough in that environment to bring back the data that will finally definitively say what the cloud layer contains. Until then, the planet keeps its clouds close. It reflects the sunlight. It gives nothing away. Why do we care so much about Venus? The answer is not Venus itself, or rather, it is not Venus alone. The answer is that Venus is one of the few natural experiments in planetary science where we can observe the outcome of a different set of initial conditions operating on a planet that started, as nearly as we can tell, very similar to our own. Earth and Venus are not just neighbors, they are, in the deepest sense, comparisons. And the comparison is instructive in ways that go beyond academic interest. Climate modeling of Venus, understanding why its greenhouse effect became runaway while Earth's did not, directly informs the models used to predict how Earth's climate responds to changes in atmospheric composition. The physical processes are the same, the equations are the same. Venus is, in a very real sense, a calibration point for climate science, a planet where we know what happened, even if we do not yet fully understand all the mechanisms, and where the outcome, sulfuric acid clouds, no liquid water, surface temperatures that melt metal, serves as an extreme end member for the range of possible outcomes of greenhouse warming on a rocky planet. Beyond climate, Venus informs the study of planetary interiors. Its lack of a global magnetic field, the result of its slow rotation, and perhaps its dry mantle, demonstrates how a planet similar to Earth in size and mass can end up without the protective magnetic shield that deflects the solar wind from Earth's atmosphere. Whether the absence of a magnetic field contributed to Venus's atmospheric evolution by allowing solar wind to strip hydrogen from the upper atmosphere more efficiently is an active area of research with direct implications for how we assess the habitability of exoplanets around other stars. And beyond that, Venus informs the study of life's limits. If the cloud layer of Venus turns out to be inhabited, or even if it turns out not to be, but the investigation produces a detailed understanding of what the chemical environment there looks like and why life cannot exist in it, that knowledge will sharpen the criteria used to assess potential habitability in atmospheres of planets beyond our solar system. As telescope technology improves and the first atmospheric characterizations of Earth-sized exoplanets become possible, knowing what an inhabited atmosphere looks like versus an uninhabited one becomes essential for interpreting the observations. Mars is often cited as the other major example of planetary divergence, but Mars diverged from Earth in a different direction and through different mechanisms. Mars lost its atmosphere primarily because it is small, too small to maintain the internal heat and magnetic field that would have protected it from atmospheric stripping by the solar wind. Mars's story is about smallness and the loss of geological activity. Venus's story is about something more subtle and in some ways more alarming. Venus is not small, it is almost exactly Earth's size. It lost its habitability not because it was too small to maintain the necessary conditions, but because it was in a slightly different location, and because those slightly different conditions triggered a feedback process that dismantled everything. That is not a story about a failed planet. It is a story about a narrow margin. The margin between the habitable and the uninhabitable, as Venus demonstrates, is not wide. It is not a comfortable buffer of millions of years and dramatic warning signs. It is, at least in the context of one of the best natural examples we have, something that operated over geological timescales. Billions of years of plausible stability, followed by a transition driven by the slow brightening of a star and the inadequacy of a geological regulation mechanism. Venus narrows the uncertainty. It tells us that 1.08 AU for a star like ours is not stably, permanently habitable over the long term. It tells us that the inner edge of the habitable zone around a solar-type star is somewhere between the orbits of Venus and Earth, and that the mechanisms controlling where exactly that edge falls involve feedback processes in atmospheric water vapor, volcanic carbon dioxide cycling, and the interaction of solar ultraviolet radiation with the upper atmosphere. It tells us, in other words, where the line is. Not precisely, not yet, but it gives us a boundary, a constraint, a data point in the search space for where in the galaxy planets like Earth might exist. And that is why Venus, despite its hostility, despite its crushing atmosphere and its surface hot enough to melt most metals, Venus is one of the most important objects in the solar system. Not because it is habitable, because it almost was. And because the distance between almost and actually, measured in planetary histories and atmospheric chemistry and orbital mechanics, is exactly the question that defines where life can exist in the universe. It has been asking the same question for 4 billion years. We are only now learning how to hear it. The surface of Venus has not been visited by a functioning spacecraft since 1985. That year, the Soviet Vega 1 and Vega 2 missions each deployed a lander onto the Venusian surface as part of a dual-purpose mission that also included atmospheric balloons and a flyby trajectory toward Halley's Comet. The Vega landers survived on the surface for approximately 20 to 56 minutes before the heat and pressure ended their transmissions. They measured surface temperatures and pressures consistent with earlier Venera data. They confirmed the basaltic composition of the surface rocks at their landing sites through X-ray fluorescence analysis. And then, like every spacecraft that had preceded them onto that surface, they fell silent. 40 years have passed since then. No lander has touched the surface of Venus in 4 decades. No instrument has directly sampled its rocks. No camera has looked across its plains in real time. What we know about the surface comes from the radar maps made by Magellan in the early 1990s, from the Soviet lander data collected across roughly 24 minutes at a handful of locations, and from remote spectroscopic and thermal observations made from orbit or from Earth. For a planet that may hold fundamental answers about planetary evolution, climate science, and the limits of habitability, that is a remarkably thin observational record. The geological story of Venus, what the surface is made of, how old its different regions are, what processes are currently reshaping it, is known only in outline. The details are missing. And the details in planetary science, as in most sciences, are where the real understanding lives. Consider the tesserae. These ancient, highly deformed terrain units, covering approximately 8% of the Venusian surface, are the oldest exposed geological material on the planet. They predate the most recent volcanic resurfacing event, and potentially preserve a record of the surface and atmospheric conditions that existed on Venus before the catastrophic volcanism that remade the planet. If the tesserae contain carbonate minerals, minerals formed by the reaction of carbon dioxide or water with calcium or magnesium-bearing rocks, that would be evidence of past water. Carbonates require liquid water and a carbon dioxide atmosphere to form through standard geochemical processes, and their presence in ancient surface rocks would confirm, through direct mineralogical evidence, what the isotopic record of the atmosphere has long suggested: water existed on Venus. If the tesserae do not contain carbonates, if they are composed entirely of anhydrous silicate minerals with no evidence of water-mediated alteration, that would also be informative. It would suggest either that the water never reached this terrain, or that the high-temperature environment has since destroyed the mineral record of its presence. Either way, the tesserae are the key to reading Venus's geological memory. The Da Vinci mission's probe is targeted to descend through the atmosphere above the Alpha Regio Tessera highland, and during the final few kilometers of its descent, image the surface at resolutions high enough to identify geological features at the meter scale. Simultaneously, its spectrometers will be sampling the atmosphere at each altitude, building up a chemical profile of the column from the cloud base to the surface. Veritas will map the entire surface at radar resolutions, several times better than Magellan, and its infrared spectroscopy will characterize the mineralogy of the surface, globally, not at the detail level of a direct sample, but at a resolution and coverage that no previous mission has achieved. The Envision mission adds a third dimension. From its orbit, it will conduct a systematic radar survey of the surface with even higher resolution than Veritas in targeted regions, and its spectrometers will characterize both the surface mineralogy and the atmospheric chemistry at a level of detail that the Venus Express mission, working with an older instrument suite, could not achieve. Together, these three missions represent the most comprehensive investigation of Venus ever planned, and they are coming, in planetary science terms, relatively soon, within the next 10 to 15 years. Understanding the mechanisms that drove Venus's transition from potentially habitable to furnace in detail, not just in outline, is the scientific goal that motivates this new wave of missions. And among those mechanisms, the behavior of the Venusian interior is one of the least understood. The interior of Venus has never been directly sampled. No seismometer has ever operated on its surface. No heat flow measurement has ever been made. The internal structure of Venus, the thickness of its crust, the depth and properties of its mantle, the size and state of its core, is inferred almost entirely from the planet's bulk density, its moment of inertia, and comparisons with Earth's interior structure. Based on these comparisons, Venus almost certainly has a differentiated interior, similar to Earth's: a dense iron-nickel core, a silicate mantle, and a basaltic crust. The core radius is estimated to be approximately 3,000 to 3,200 kilometers, similar in proportion to Earth's. Whether the core is liquid or solid, whether it has a fluid outer core analogous to Earth's, whose convective motion generates the magnetic field, is not known. The absence of a global magnetic field on Venus suggests that either the core is not convecting, or that the convective motion is too slow or too uniform to generate a self-sustaining dynamo. Both possibilities are consistent with Venus's slow rotation, which provides less Coriolis force to organize the convective flow into the kind of structured helical patterns that are thought to be necessary for dynamo action. Earth's magnetic field is generated by the combination of core convection and rotational forcing. Venus, rotating 60 times more slowly, may simply not have enough rotational forcing to organize its core convection into a dynamo configuration. If this interpretation is correct, the absence of Venus's magnetic field is ultimately traceable to the same feature that has shaped so much of the planet's character: its anomalous rotation, the retrograde rotation, the slow spin, the 243-day day. These are not merely curiosities. They are conditions with deep consequences for the planet's internal dynamics, its atmospheric circulation, its thermal balance, and ultimately its geological and climatic evolution. Everything connects. The rotation shaped the core dynamics, which determined the magnetic field, which affected the solar-wind interaction, which influenced the rate of atmospheric escape. The rotation shaped the atmospheric circulation, which drove the superrotation, which controlled the cloud layer dynamics, which affected the albedo and the temperature structure. A planet is not a collection of independent systems. It is an integrated system where the initial conditions set billions of years ago, the mass, the composition, the orbital parameters, the rotation rate inherited from the physics of the accretion disk, propagate forward in time through coupled physical processes and determine gradually what the planet becomes. Venus became what it is because of where it was, how fast it was spinning, what its mantle was made of, and how much water it started with. Change any one of those factors significantly, and the outcome might have been different. We got the current Venus. And the current Venus is, in its own way, a kind of answer, an answer to the question of what happens when the conditions do not align for long-term habitability, when the margin is not quite wide enough, when the feedback loops run in the wrong direction. It is a complete answer in the sense that the planet has fully committed to its trajectory, and there is nothing ambiguous about where it ended up. Venus continues on its orbit, maintaining its surface, circulating its sulfuric acid clouds at 100 meters per second in the upper atmosphere. It has been doing this for hundreds of millions of years. It will continue doing it for billions more. There is one more dimension of the Venusian story that deserves attention before we turn to the texture of the surface itself. It is the dimension of time, not geological time, but the time of human engagement with Venus, the time of the telescopes and the spacecraft and the scientists who dedicated careers to understanding a planet that systematically destroyed every instrument sent to its surface. It starts with Galileo. In 1610, Galileo Galilei turned his telescope toward Venus and observed something unexpected. Over a period of weeks and months, the apparent disk of Venus changed shape. It went from a small, nearly full circle to a large crescent, the same pattern of phases that the moon goes through, but with a striking additional feature. As the phase decreased from full toward crescent, the apparent size of the disk increased. This observation, phases of Venus combined with a change in apparent size, could only be explained by one geometrical arrangement. Venus had to be orbiting the Sun, and at different points in its orbit, it was at different distances from Earth. When nearly full, it was on the far side of the Sun, small and distant. When a thin crescent, it was on the same side as Earth, large and close. This was direct observational evidence against the Ptolemaic geocentric model of the solar system. Galileo understood what he was seeing. The phases of Venus were observational confirmation that Venus orbited the Sun, and by extension that the heliocentric model of Copernicus was at least partially correct. This observation, made in the cold winter nights of early 17th century Italy through a telescope with an objective lens a few centimeters across, was the first scientific contribution of Venus to the reorganization of human understanding of the cosmos. Nearly 5 decades later, in 1761, another observation of Venus contributed another piece of fundamental knowledge. The English astronomer Edmund Halley had predicted, decades earlier, that observations of a transit of Venus, the passage of Venus across the disk of the Sun from widely separated locations on Earth, could be used to determine the distance between Earth and the Sun, the so-called astronomical unit. In 1761, an international scientific effort, one of the first globally coordinated scientific enterprises in history, sent observers to dozens of locations around the world to record the Venus transit. The results were imperfect, hampered by an atmospheric optical effect called the black drop effect, in which Venus appeared to cling to the solar limb as it entered and exited the disk, making precise timing difficult. But the 1769 transit produced cleaner results, and from the combined data, astronomers derived a value for the astronomical unit of approximately 153 million kilometers, within 2% of the modern accepted value of 149.6 million kilometers. Venus, simply by passing in front of the Sun, taught humanity the scale of the solar system. 2 centuries later, in the 1960s, radar observations from Earth provided the first direct measurement of Venus's distance at a specific moment, allowing a much more precise determination of the astronomical unit. And those radar observations also produced the first clear measurements of Venus's rotation rate, the anomalously slow, retrograde rotation that has been central to so much of what followed. The history of Venus knowledge is, in this sense, a history of successive surprises. Every time the technology improved enough to look at the planet in a new way, what was found was unexpected. Galileo's phases, Halley's transit, the radar rotation measurement, the atmospheric temperature and pressure from the Venera program, the surface photographs, the Magellan topography, the phosphine detection. Each of these was, at the moment of discovery, a surprise. Each revised, sometimes dramatically, what science thought it knew about the planet. And the pattern of improvement in observational capability, followed by surprise, followed by revision of understanding, is almost certainly not finished. The next generation of missions will look at Venus with instruments several times more capable than anything previously deployed there. They will sample environments that no previous mission has reached. They will measure chemical species at sensitivities that would have been technologically impossible even 20 years ago. And they will almost certainly find things that are unexpected. That is not a prediction about any specific discovery. It is a statement about the pattern. Venus has surprised us every time we have looked at it carefully. What is different this time is that we are looking with specific questions already formed. Questions about the tessera mineralogy, about the volcanic activity rate, about the atmospheric phosphine, about the habitability of the cloud layer. We are not looking blind, as Galileo was when he turned his telescope toward a point of light and found phases. We are looking with hypotheses, with models, with predictions that specific measurements should either confirm or refute. That is how science matures, not by replacing curiosity with certainty, but by replacing open-ended wonder with directed inquiry by knowing enough to ask specific questions and then designing instruments capable of answering them. Venus has given us enough of its story across 4 centuries of observation to formulate those specific questions. The answers are now within reach. The science has established the parameters. Now it is time to inhabit them. The surface that the next generation of instruments will study has not changed since the last spacecraft landed there in 1985. It will not have changed when the next one arrives. That constancy, that geological and atmospheric permanence on human timescales, is itself a quality worth acknowledging. Venus is not comfortable, but it is consistent. It will be 100 years from now, within a degree or two of the same temperature, within a fraction of a percent of the same atmospheric pressure. The same clouds, circling at the same speed, carrying the same chemistry, in the same endless 4-day loop. A century from now, 1,000 years from now, 10,000. The planet's geological timescale dwarfs anything human civilization has yet experienced. The most recent volcanic resurfacing event on Venus occurred more than 300 million years ago, roughly the same time that the first reptiles were appearing on Earth, and more than 298 million years before the first member of the genus Homo walked on any landscape anywhere. From Venus's perspective, if a planet can be said to have a perspective, the entire history of human civilization, from the first cities to the current moment, is a single, imperceptibly brief instant in a story that has been running for 4 billion years and will continue running for several billion more. The gap between the last lander in 1985 and the next one in the 2030s is not for lack of scientific interest. It is because the engineering problem of surviving on the surface of Venus, not for 127 minutes, but for hours or days, has not yet been fully solved. The materials and cooling technologies available for the Venera missions were sufficient for those brief survival windows. Building a lander that could operate for a full day on the Venusian surface, long enough to take a seismic measurement, to drill into a rock and analyze it, to set up atmospheric monitoring equipment and let it run, requires a different class of engineering. That class of engineering does not yet exist in fully demonstrated form, but it is being developed. NASA's Glenn Research Center has been conducting research into high-temperature electronics capable of operating at Venus surface temperatures without active cooling, using silicon carbide semiconductor technology that remains functional at temperatures up to 500 degrees Celsius. Laboratory demonstrations of simple circuits operating at Venusian surface temperatures have been conducted. The gap between a laboratory circuit demonstration and a fully functional spacecraft instrument suite is large, but the principle has been proven. Several proposed mission concepts, not yet funded or approved, but explored in detail in scientific literature and mission study reports, envision long-lived Venus surface stations capable of operating for weeks or months, using high-temperature electronics, passive thermal management, and potentially novel cooling approaches. A seismometer on the surface of Venus, operating for months, could characterize the planet's internal structure by recording seismic waves from the internal tremors generated by ongoing geological activity, combined with surface magnetic field measurements and heat flow data. A long-lived Venus surface station could provide the first direct constraints on the internal structure and thermal state of the planet. This is what is at stake in the next phase of Venus exploration. not just answering questions about this particular planet, but developing a framework for understanding rocky planet evolution that is currently incomplete in fundamental ways, because the only rocky planet with a well-characterized interior, well-understood geological history, and well-sampled surface environment is Earth, and Earth cannot serve as its own control. Venus is the comparison case, the near-identical twin that went a different direction, whose internal structure and geological history and atmospheric chemistry, measured and characterized and compared to Earth's, will fill in the blanks in the theory of rocky planet evolution that Earth alone cannot fill. This is not a story that ends with the current knowledge. It is a story in progress. Venus is in progress. And as the night deepens and the specifics of temperatures and pressures and geological timescales begin to blur at the edges, as the numbers soften into impressions and the impressions soften into something more diffuse, what remains is not the data, but the quality of the place. A world of almost Earth-sized, almost as massive, almost in the same region of the solar system, almost, perhaps, habitable once. A world that has been burning for hundreds of millions of years and has not stopped. A world where the clouds never part, where the surface never cools, where the sun rises in the wrong direction and the day is longer than the year. The parameters are known. The implications are not fully resolved. The planet is patient. And in that patience, in the absolute geological stillness of a world that has committed fully to whatever it has become, there is something that functions in its own inhuman way as a kind of completeness. Not comfort, not beauty in any conventional sense. Completeness. A thing that is entirely itself, a world that has followed its physics all the way to its logical conclusion and arrived at a state of extreme, stable, coherent hostility. The laws did not change, the planet did. And now, in the long, patient orange twilight of its current state, it carries everything it has ever been: the early warmth, the lost ocean, the crashed spacecraft, the radar echoes of 1,000 mapped features, as geological and atmospheric memory waiting for instruments sensitive enough to read it. The science has established the parameters. Now it is time to inhabit them. The surface of Venus has a temperature of 465 degrees Celsius, a pressure equivalent to 900 meters of ocean, and an atmosphere of 96.5% carbon dioxide, moving at 0.5 to 3 meters per second across basaltic plains under an orange, sourceless sky. These are not abstractions, they are the specific physical conditions of a place that has existed in this state for hundreds of millions of years. A place with a texture, a weight, a quality of light, a sound environment, a chemical environment so corrosive that any organic material exposed to it would begin reacting immediately. This is what the Venera landers entered. This is what those spacecraft, built to withstand conditions that their engineers could only partially model in advance, reinforced with titanium, cooled with internal refrigeration systems designed to buy minutes rather than hours, descended into, one by one, across the decades of the Soviet Venus program. They entered the upper atmosphere at velocities of several kilometers per second, slowed first by parachutes in the upper cloud deck, then by aerodynamic drag in the lower atmosphere, then by small retrorockets in the final hundreds of meters above the surface. The descent took approximately 1 hour from atmospheric entry to surface contact. During that hour, the temperature outside the spacecraft rose from the near vacuum cold of interplanetary space to the full 465 degrees of the surface, and the pressure increased from essentially 0 to 92 bars. The cooling systems inside the landers fought this thermal assault continuously. They were not designed to win, they were designed to delay. The Venera 13 lander, which touched down on March 1st, 1982, in the volcanic plains of the Phoebe Reggio region, was expected to survive approximately 32 minutes on the surface. It survived for 127 minutes, 4 times the design specification. During that time, it transmitted color photographs of the surface, conducted a soil analysis using an X-ray fluorescence spectrometer, recorded audio of the surface environment, and transmitted a comprehensive set of atmospheric measurements taken during the descent. The photographs returned by Venera 13 are among the most remarkable images in the history of planetary exploration. They show a surface of flat, interlocking slabs of dark rock, fine-grained basalt, as the chemical analysis confirmed, surrounded by loose, granular material that may represent weathered rock fragments or volcanic ash. The slabs have relatively sharp edges, as earlier Venera missions had shown, with limited evidence of physical erosion. The surface stretches away from the lander in all directions until it disappears into the haze of the dense lower atmosphere. The horizon is close, no more than a few kilometers, given the low altitude and the atmospheric opacity. The sky above, visible in the upper portions of the images, shows the diffuse illumination that characterizes the Venusian atmosphere at the surface, a sourceless, omnidirectional light that does not cast hard shadows because the light source is not a direct solar disk, but the entire hemisphere of glowing, scattering atmosphere above. The color in the images is orange-brown, which partially reflects the actual color of the light, the red-orange filtering of the atmosphere, but also partially reflects the fact that the Venera color calibration targets were not perfectly corrected for the specific spectrum of Venusian surface illumination. Post-processing of the Venera images with corrected color calibration suggests that the surface rocks are actually a darker gray-brown color than the orange-tinted original photographs suggest. The atmosphere does impart an orange cast to the light, but the rocks themselves, in their actual physical state, are likely the dark gray characteristic of unweathered basalt, the same color as fresh lava on the flanks of a Hawaiian shield volcano or on the floor of a mid-ocean ridge. The audio recorded by Venera 13, the first ever audio recording from the surface of another planet, consisted primarily of the sounds of the lander itself, the mechanisms of the instruments deploying, the vibrations of the spacecraft structure, but it also captured something of the ambient sound environment. The dense Venusian atmosphere transmits sound efficiently, more efficiently than Earth's atmosphere, because the higher density increases the acoustic impedance. Sounds that would be faint in Earth's air would carry farther and with more energy in Venus's lower atmosphere, but the surface environment was apparently quiet. No wind gusts loud enough to register distinctly. No geological sounds from the surface. The ambient noise floor was low. A geologically active planet, in the moment of this observation, was simply not being loud about it. Later Venera missions, Venera 14, which landed 4 days after Venera 13, confirmed the basaltic surface composition and extended the record of surface imagery to a second location, also in the lowland volcanic plains. The two sites were several thousand kilometers apart, but showed broadly similar terrain, dark, flat-slabbed rock extending to the limits of visibility in the orange-tinted haze. Together, the Venera Image Archive, approximately a dozen photographs from 3 successful imaging landers, constitutes everything humanity has ever directly seen of the Venusian surface, not simulated, not modeled, not inferred from radar data, actually photographed from instruments sitting on the ground with cameras pointed outward at a landscape no human eye has ever observed directly. Those images are publicly available. They can be found in the archives of the Russian space program and in scientific literature repositories. They are small, low resolution by modern standards, and heavily processed. But they are real. They show an actual place. They are the only visual record of a world that is, in almost every physical sense, utterly different from the one visible through any window on Earth tonight. Looking at them is a strange experience. The surface they show is not dramatic in the way of a Martian impact crater or a Jovian storm system. It is in many ways quiet, a flat plain of dark rock under a hazy orange sky, stretching away in all directions with no visible features of dramatic scale in the immediate vicinity of the landers. The rocks are unremarkable in their geometry. The light is dim, and yet the context transforms the image entirely. That flat, ordinary-looking plain is at 465 degrees Celsius. The air above those rocks is carbon dioxide at 92 times the pressure of Earth's atmosphere. The haze in the distance is not water vapor, but the dense lower atmosphere of a greenhouse-locked planet. The light arriving from above has passed through 65 kilometers of sulfuric acid clouds. The surface beneath those rocks has not been touched by liquid water for perhaps 2 billion years. The ordinariness of the visual scene and the extremity of the physical conditions create a kind of cognitive dissonance that is difficult to resolve. It looks like somewhere a person could stand. It looks, in the dim orange light, almost like a twilight landscape on an overcast evening on Earth. The rocks could be rocks from a quarry. The haze could be distance. But nothing about it would be survivable, not for a second. The heat alone, 465 degrees, is well above the ignition point of paper, of wood, of most fabrics, and is sufficient to cause severe burns to any exposed surface of a biological organism before the thermal equilibrium is even approached. The pressure at 92 bars would compress any gas-filled space in a human body, lungs, sinuses, middle ear, to a tiny fraction of its normal volume, and would drive the dense carbon dioxide atmosphere through any tissue with pores or passages. The chemical composition would react with biological material. The absence of oxygen would eliminate any possibility of aerobic metabolism. The surface of Venus is not simply hostile. It is, from the perspective of Earth biology, absolutely and completely incompatible with life as we understand it. And yet it was there, at this specific time in 1982, that Venera 13 sat for 127 minutes, its cooling systems running, its instruments sampling, its cameras taking photographs, and transmitting them back across 88 million kilometers to the antennas that were listening. The spacecraft was built in Leningrad, assembled by engineers who had spent years learning from each previous mission's failure, launched on a Proton rocket in October 1981, 5 months before it arrived. It weighed approximately 760 kilograms at launch, though much of that mass was the protective aeroshell and descent systems that were jettisoned or burned off during the approach. The lander itself, the part that touched the ground, weighed approximately 400 kilograms. It was less than 1.5 meters tall. A 400-kilogram sphere of titanium sitting on a plane of basalt at 465 degrees, sending photographs of the view. For 127 minutes. And then silence. The engineering work that made those 127 minutes possible is in its own way as remarkable as any of the science the mission returned. The problem of surviving on the surface of Venus is not primarily a problem of materials, though materials are challenging. It is a problem of thermodynamics. Heat flows from hot regions to cold regions. At 465 degrees, the surface of Venus is trying to heat everything it is in contact with. The only way to keep the instruments inside the lander cool enough to function is to slow the rate at which heat flows from the exterior to the interior. This is done through insulation, minimizing thermal conductivity at the spacecraft wall, and through thermal mass. The body of the lander acts as a heat sink. It absorbs the incoming thermal energy from the surface environment, and because it has a finite thermal mass, it heats up slowly. The instruments inside are protected by this slow heating. Eventually, the temperature inside the spacecraft reaches the limit of instrument operation, somewhere around 200 degrees Celsius for the most sensitive electronics, and the mission ends. The engineers calculated the thermal mass needed to provide a specific survival time. They added margin. Venera 13 survived 4 times its design specification, which means either the actual surface conditions were slightly less severe than the design case, or the thermal model underestimated the insulation performance, or some combination of both. Whatever the reason, the lander performed beyond expectations, and the additional time it bought was used fully. The instruments continued operating until the signal finally ceased. Those 127 minutes are the longest any spacecraft has ever functioned on the surface of Venus. Since 1985, no spacecraft has landed there. The gap is not for lack of scientific interest. It is because the engineering problem of surviving on the surface of Venus, not for 127 minutes, but for hours or days, has not yet been solved. The materials and cooling technologies available for the Venera missions were sufficient for those brief survival windows. Building a lander that could operate for a full day on the Venusian surface, long enough to take a seismic measurement, to drill into a rock and analyze it, to set up atmospheric monitoring equipment and let it run, requires a different class of engineering. That class of engineering does not yet exist in fully demonstrated form, but it is being developed. NASA's Glenn Research Center has been conducting research into high-temperature electronics capable of operating at Venus surface temperatures without active cooling, using silicon carbide semiconductor technology that remains functional at temperatures up to 500 degrees Celsius. Laboratory demonstrations of simple circuits operating at Venusian surface temperatures have been conducted. The gap between a laboratory circuit demonstration and a fully functional spacecraft instrument suite is large, but the principle has been proven. Several proposed mission concepts, not yet funded or approved, but explored in detail in scientific literature and mission study reports, envision long-lived Venus surface stations capable of operating for weeks or months, using high-temperature electronics, passive thermal management, and potentially novel cooling approaches that do not rely on the conventional phase change refrigerants that the Venera missions used. A seismometer on the surface of Venus, operating for months, could characterize the planet's internal structure by recording seismic waves from moonquakes, or rather from Venusquakes, the internal tremors generated by ongoing geological activity. Combined with surface magnetic field measurements and heat flow data, a long-lived Venus surface station could provide the first direct constraints on the internal structure and thermal state of the planet, data that would transform the understanding of why Venus evolved so differently from the Earth and whether similar divergence could occur on planets around other stars. This is what is at stake in the next phase of Venus exploration. Not just answering questions about this particular planet, but developing a framework for understanding rocky planet evolution that is currently incomplete in fundamental ways, because the only rocky planet with a well-characterized interior, well-understood geological history, and well-sampled surface environment is Earth, and Earth cannot serve as its own control. Venus is the control. Or rather, Venus is the comparison case, the near-identical twin that went a different direction, whose internal structure and geological history and atmospheric chemistry, measured and characterized and compared to Earth's, will fill in the blanks in the theory of rocky planet evolution that Earth alone cannot fill. The Venera 13 photographs sit in the archive. The instruments have been silent for more than 40 years. But the surface they photographed is still there. The slabs of dark basalt are still there at 465 degrees under the orange sky in the dense carbon dioxide atmosphere, surrounded by the slow-moving lower atmosphere winds. They will still be there when the next lander arrives. And the next lander, whenever it comes, will find them unchanged, because a surface at 465 degrees, under 92 bars of carbon dioxide, and the complete absence of water, weathers so slowly that the timescale of significant erosion is measured in tens of millions of years. The rocks photographed in 1982 will look the same in 2082, in 2182, in 2282. Venus is patient in a way that geology enables and thermodynamics enforces. It will wait. The mountains of Maxwell Montes rise 8 kilometers above the plains, taller than any mountain on Earth when measured from the surrounding terrain. Their slopes reflect radar in a way that suggests metallic mineral deposits, possibly bismuth sulfide or lead sulfide or other compounds that condense at the slightly lower temperatures found at higher altitudes, creating what has been described as a metallic snow line, an elevation above which the temperature drops enough for certain vapor phase metal compounds to condense onto the rock surfaces as a thin, shiny coating. Metal snow on a mountain made of rock, on a planet with no water, under clouds made of acid. The physics is the same physics that operates everywhere in the universe. Condensation of a substance occurs when temperature drops below the dew point, or in this case, the sublimation point, of that substance. On Earth, water condenses on cold surfaces and falls as rain or snow. On Venus, metal compounds condense on cool highland surfaces and form a reflective coating. The mechanism is identical. The substance is radically different. That is Venus in miniature, the same physics, a different chemistry. The same laws operating under different boundary conditions and producing a world that is, from the outside, almost unrecognizable, but which, from the inside, from the perspective of the equations, makes complete and coherent sense. Everything that Venus is follows from what Venus started as, and from what it has been through. The laws did not change, the planet did. And now, in the long, patient orange twilight of its current state, it carries everything it has ever been: the early warmth, the lost ocean, the crashed spacecraft, the radar echoes of 1,000 mapped features, as geological and atmospheric memory, waiting for instruments sensitive enough to read it. The mountains are there. The metallic snowline is there. The basalt plains are there. The remnant isotopic signature of an ocean that ended 2 billion years ago is there, encoded in the ratio of 2 hydrogen isotopes in the trace water vapor of the upper atmosphere. It is all still there, patient and complete and silent under the moving clouds in the dim light that filters down from a sun it cannot clearly see. There is a region on Venus called Lakshmi Planum. It sits within the larger highland area known as Ishtar Terra, the continent-scale elevated terrain in the northern hemisphere of the planet, named for the Babylonian goddess of love and war. Lakshmi Planum is a high plateau elevated approximately 3 to 4 kilometers above the mean planetary radius, surrounded on most sides by mountain ranges. To the east rise the Maxwell Montes. To the south and west, the Freyja and Acna mountain ranges complete a roughly circular enclosure. The plateau itself is remarkably flat by planetary standards, a broad, level surface of volcanic rock, nearly featureless in radar imagery, apparently formed by massive lava flooding that filled a pre-existing topographic basin to a nearly uniform depth. Lakshmi Planum is approximately 2,500 kilometers across. It is large enough to contain the entire continental United States, with room to spare. It sits, this enormous volcanic plateau, at an elevation where the temperature is perhaps 20 to 30 degrees cooler than the surrounding lowlands, still above 430 degrees Celsius, but fractionally more moderate. The atmospheric pressure at its surface is correspondingly lower than at the plains below, though still more than 70 bars. The metallic snowline that coats the Maxwell Montes to the east may extend down toward the plateau margins in certain seasons, though seasons on Venus, with its nearly zero axial tilt, are minimal, and the temperature variation through the Venusian year is small. Lakshmi Planum is not obviously special from a geological standpoint. It is one of many large volcanic features on a planet covered in volcanic features. Its boundaries are defined by mountain ranges that formed through crustal deformation, the same processes that produce the corrugated tessera terrain visible in other highland regions. The lava that flooded its interior came from somewhere below, from the Venusian mantle, through conduits that are no longer clearly visible in the surface imagery. But there is something about a plateau that invites consideration. A plateau is, in its simplest physical description, a high flat place. It is exposed, open to whatever environment exists above it. On Earth, high plateaus receive different weather than surrounding lowlands. The Tibetan Plateau, the Altiplano, the Colorado Plateau, each of these creates its own regional climate, its own atmospheric dynamics, its own ecological zone. The elevation changes the temperature changes the precipitation changes the rock changed rock changes the changed soil changes what can live there. On Venus, the chain of consequences from elevation is different. There is no precipitation that reaches the ground, there is no soil in the biological sense. There is no life as far as is known, but the physical consequence of elevation, cooler temperature, lower pressure, changed chemistry of the surface-atmosphere interaction is still real. The Maxwell Montes, rising to 8 kilometers above the plains, experience conditions at their summits that are meaningfully different from what the lowlands experience. The metallic snow on their slopes is evidence of that difference. What Lakshmi Planum represents in this context is a large area of Venus where the conditions are slightly, only slightly, less extreme than the mean, not habitable, not approaching habitable, but different enough to mark out a region where the chemistry of the surface-atmosphere interaction is, in some small way, distinct. That distinctiveness is worth measuring. It is worth comparing to other regions. It is worth adding to the map of what Venus actually is across its full range of surface environments, rather than treating the planet as a uniform 465-degree surface with no internal variation. Because Venus does have internal variation, the Maxwell Montes rise dramatically above the surrounding lowlands. The tesserae are older than the volcanic plains. The corona mark positions of past or present mantle plume activity. The lava channels trace routes of ancient eruption flows. Each of these features is a data point in a larger map of geological history, and taken together they tell a story, incomplete, in need of additional measurements, but recognizable as a story, about a planet that has been doing specific things in specific places for billions of years. The story is not finished. The data is not complete. The questions are not answered. But the questions, at least, are clear. They are the questions that 4 centuries of observation and 50 years of spacecraft exploration have produced. Specific, testable, answerable with the right instruments in the right places. Questions about tessera mineralogy and volcanic activity rates, and atmospheric phosphine concentrations, and interior seismic structure, and the depth of the magnetic field deficit, and the cloud layer chemistry at 55 kilometers altitude. These are questions that can be answered. Not with certainty, not with finality. Science rarely works that way, but with enough precision to replace current speculation with current constraint, and to open the next generation of questions. That is the trajectory of Venus science. From the phases in Galileo's telescope to the transit measurements of 1769, to the radar rotation measurements of the 1960s, to the Venera surface data of the 1970s and 1980s, to the Magellan radar maps of the 1990s, to the Venus Express atmospheric studies of the 2000s, to the phosphine controversy of the 2020s, and now to the missions being designed and built for the 2030s. Each step built on the last. Each surprise reoriented the questions. Each mission left the planet still mysterious, but less so, and left the mystery more precisely located, more specifically defined, more amenable to the focused inquiry of the next instrument generation. This is not a story that ends with the current knowledge. It is a story in progress. Venus is in progress. And as the night deepens, and the specifics of temperatures and pressures and geological timescales begin to blur at the edges, as the numbers soften into impressions and the impressions soften into something more diffuse, what remains is not the data, but the quality of the place. A world of almost. Almost Earth-sized, almost as massive, almost in the same region of the solar system. Almost perhaps habitable once, A world that has been burning for hundreds of millions of years and has not stopped. A world where the clouds never part, where the surface never cools, where the sun rises in the wrong direction and the day is longer than the year, and where somewhere in the acid haze at 55 kilometers altitude, something is circling that may or may not be alive. The parameters are known. The implications are not fully resolved. The planet is patient. It has been patient for 4 billion years. It will be patient for 4 billion more. And in that patience, in the absolute geological stillness of a world that has committed fully to whatever it has become, there is something that functions in its own inhuman way as a kind of completeness. Not comfort, not beauty in any conventional sense. Completeness. A thing that is entirely itself. A world that has followed its physics all the way to its logical conclusion and arrived at a state of extreme, stable, coherent hostility. Venus knows exactly what it is. In the long orange twilight of its perpetual surface, in the steady circulation of its acid clouds, in the retrograde turning of its days, it is entirely, unambiguously, completely itself. There is something almost restful about that. Not the rest of safety, not the rest of comfort. The rest of a thing that has come to a conclusion. And the conclusion, 465 degrees, 92 bars, sulfuric acid clouds, no ocean, no plate tectonics, no magnetic field, slow backwards rotation, is written in every detail of the planet, down to the metallic snow on the mountain slopes and the isotopic memory of the water that used to be there and is not anymore. All of it is the same answer to the same question, which is, what does a planet become when the conditions are almost but not quite right for something else? This is what it becomes. This. Let that sit quietly. The planet is still out there. The rocks photographed by Venera 13 in 1982 will be in the same position they were in then, within whatever tolerance the slow surface winds and the thermal expansion of the basalt allow. Unchanged. The planet turns, slowly, backwards, in the dark. And it is, in every respect, still there. The night is quieter now. Not because anything has changed in the universe. Venus is still where it was when this story began, orbiting the sun, maintaining its surface heat, circulating its clouds in their 4-day loop. The planet has not slowed. The clouds have not parted. The surface has not cooled by even a single degree. But the way of attending to it can change. The earlier parts of this story moved through data, through mechanism, through the connected chains of cause and consequence that explain why Venus is what it is, the formation of the solar system, the delivery of water, the slow brightening of the sun, the engagement of feedback loops, the loss of the ocean, the buildup of the atmosphere, the volcanic resurfacing, the Venera program, the Magellan maps, the phosphine controversy, the missions being built for the next decade. All of that is real. All of it is verified by measurements, by spacecraft, by laboratories, by the accumulated work of thousands of scientists across decades. And now, in the later hours of the night, the data can settle. It does not need to be reviewed or rehearsed. It is already there, accumulated in whatever part of the mind holds things heard in the dark, not memorized, not cataloged, but present, the way the sound of rain is present when you fall asleep to it. Not analyzed, just there. The light currently leaving the Venusian cloud tops will reach Earth somewhere between 2 and 14 minutes from now, depending on where in its orbit Venus sits. That light, reflected sunlight scattered back from the sulfuric acid cloud deck that gives the planet its extreme albedo, is the same light that makes Venus the brightest natural object in the sky after the sun and the moon. When Venus appears in the evening sky just after sunset, ancient cultures called it the evening star. When it appeared before sunrise, they called it the morning star. For a long time, it was not understood that these were the same object. The Greeks had two names for it: Hesperus in the evening, Phosphorus in the morning, and it was the Pythagorean philosopher Parmenides, or possibly the astronomer Epicus, who first argued, sometime in the 5th or 6th century BCE, that both apparitions were the same planet, not a star at all. A planet, moving in its own orbit, appearing on different sides of the sun at different times of the Venusian year, sometimes preceding the sun into the morning sky, and sometimes following it into the evening. The naming conventions settled on Venus, the Roman goddess of love, beauty, and desire, the brightest light in the sky after the sun, the one that outshines everything else. The name predates the knowledge by 2,000 years. No one who named it Venus knew what was below the clouds. No one who watched it blaze in the evening sky could have guessed at 465 degrees, at 92 bars, at the sulfuric acid content of the cloud layer they were admiring. The beauty of Venus from Earth's surface is real, a stable, unwavering point of brilliant white-yellow light, often the first star-like object visible in the twilight, sometimes bright enough to cast a faint shadow on a dark night. That beauty is entirely a function of the albedo. Venus is bright because it reflects so much light. It reflects so much light because its clouds are so thick and so continuous. Its clouds are so thick because the atmosphere is so massive. The atmosphere is so massive because the greenhouse effect drove the surface temperature to a point where no silicate weathering or ocean chemistry can remove carbon dioxide from the system. The greenhouse effect is that extreme because the water that would have moderated it was lost billions of years ago. The beauty of Venus, as seen from Earth, is the end result of a chain of catastrophes. Seen clearly, it is still beautiful. The light does not change because of what produced it. Let the light be what it is. The planet turns in its slow retrograde rotation, 243 days to complete one full spin, the sun rising in the west, crossing the sky over the course of the long Venusian day, a day-long arc that takes 58 Earth days to complete, from the western horizon where it rises to the eastern horizon where it sets, if the clouds were not there to obscure it entirely. The sun is not visible from the surface of Venus, not directly. It is a brightness in the cloud layer above, a diffuse sourceless illumination that arrives from the upper hemisphere without the sharp disk that makes a sun identifiable. The light is orange. It is everywhere and nowhere. It casts no hard shadows. In this dim, omnidirectional orange light, the volcanic plains extend in every direction. The Maxwell Montes are several thousand kilometers to the north of the volcanic lowlands, their summits at 8 kilometers altitude, coated in metallic mineral condensates that reflect the subdued light back with a faint metallic sheen. From the plains below, they would not be visible. The atmosphere is too opaque, the distance too great, the the scale of the terrain too vast for any single viewpoint to take in. Venus reveals itself not to any observer standing on its surface, but to instruments in orbit, to radar pulses bouncing from above, to the patient accumulation of data across years of mapping. The planet is not designed for observers. It is designed by physics. And physics, in this case, has produced a surface that no organic observer will stand on for a very long time, perhaps ever, given the engineering challenges involved. The surface of Venus is one of the few places in the solar system that is genuinely beyond the reach of human presence in any practical sense. Mars is difficult and dangerous and cold, but it is in principle reachable with sufficient life support. The Moon is reachable and has been reached. The asteroids are accessible. The Jovian and Saturnian moons present extreme challenges, but are being planned for in the longer term. The surface of Venus presents a different category of challenge. Not the cold of space, not the vacuum, not the radiation of the outer solar system, but heat and pressure combined in a way that defeats every material solution currently available, that overwhelms every cooling system, that gives any instrument a survival window measured in minutes rather than months. The next lander on Venus will survive for hours if the high-temperature electronics research succeeds. Perhaps a day, perhaps several days. And then it too will fall silent. The planet will still be there after it falls silent. It will still be at 465 degrees. The clouds will still be circling. The retrograde rotation will still be carrying the sun from west to east across the cloud-covered sky. And the next instrument, whenever it arrives, will find the surface exactly as it was when the last one fell silent. That constancy, that geological and atmospheric permanence on human timescales is itself a quality worth acknowledging. In a world of rapid change, of seasons and weather and the constant movement of living things, there is something to be said for a place that simply does not change on any timescale a human life can measure. Venus is not comfortable, but it is consistent. It will be 100 years from now, within a degree or two of the same temperature, within a fraction of a % of the same atmospheric pressure, the same clouds circling at the same speed, carrying the same chemistry, in the same endless 4-day loop. A century from now, 1,000 years from now, 10,000. The planet's geological timescale dwarfs anything human civilization has yet experienced. The most recent volcanic resurfacing event on Venus occurred more than 300 million years ago, roughly the same time that the first reptiles were appearing on Earth, and more than 298 million years before the first member of the genus Homo walked on any landscape anywhere. From Venus's perspective, if a planet can be said to have a perspective, the entire history of human civilization, from the first cities to the current moment, is a single, imperceptibly brief instant in a story that has been running for 4 billion years and will continue running for several billion more. That span of time is difficult to hold in the mind. Not impossible, but difficult. The way to approach it is not to try to comprehend the whole span at once, but to let it pass, to let it be what it is, a number too large for intuitive grasp, and to rest in the fact of it without trying to fill it with content or imagery. 4 billion years. Just let that be a phrase for a moment, not a calculation, a sound. 4 billion years. The planet has been turning for that long. The sun has been shining on it for that long. The internal heat has been driving the geological processes for that long. Whatever Venus was in the beginning, that forming, accreting, differentiating body of rock and metal and volatile compounds, assembling itself from the debris of the solar nebula, it has been continuously becoming something ever since. And what it has become through all of that becoming, through the early oceans and the feedback loops and the lost water and the volcanic resurfacing and the thick toxic atmosphere that now defines it, is the specific Venus that exists tonight. Not a warning, not a tragedy, not a cautionary tale. A planet. A specific, physical, chemically and geologically active world that is exactly what 4 billion years of physics has produced from its particular starting conditions. It is complete. In the way that a deep ocean trench is complete, or a desert is complete, or a vacuum is complete, not complete in the sense of finished, because geological and atmospheric evolution will continue, but complete in the sense of being entirely and coherently what it is. Nothing about Venus is approximate or provisional. Its temperature is what it is. Its pressure is what it is. Its clouds are what they are. Its rotation is what it is. The isotopic signature of its lost ocean is what it is. The planet has committed. There is a particular quality to the kind of quiet that comes from contemplating something that has committed this fully to being what it is. It is not the quiet of emptiness, not the quiet of absence. It is the quiet of a thing that has arrived, through billions of years of process, through feedback loops and geological events, and the slow brightening of a star at what it is going to be, at least for the next several billion years. Let that quality of quiet come forward now. Not Venus as a problem to be solved or a question to be answered. Not Venus as a reference point or a lesson. Just Venus, maintaining its clouds, reflecting its light, turning slowly in the wrong direction. The light that Venus is reflecting right now has been traveling since it left the sun approximately 6 minutes ago. It struck the top of the Venusian cloud layer and was scattered back into space in all directions simultaneously, a portion of it heading toward Earth, where it will arrive in another few minutes, where it will enter whatever telescope or naked eye is pointed in the right direction, and complete its journey as a point of light in someone's field of view. The same photon that scattered off a sulfuric acid droplet at 65 kilometers altitude over Venus will end its journey somewhere here on Earth. The same physics that makes Venus visible makes it comprehensible. The same laws that govern the greenhouse effect on Venus govern the infrared absorption in Earth's atmosphere. The same orbital mechanics that determined Venus's distance from the Sun determined Earth's. There is no separation between the understanding of Venus and the understanding of home. They are the same understanding, applied to different conditions, different outcomes from the same laws. That is what makes Venus worth thinking about as the night deepens and the day's concerns recede, and the mind becomes receptive to larger scales of time and distance. Not the specific data points, the 465 degrees, the 92 bars, the 96.5% carbon dioxide. Those are real and important, and they are all correctly filed wherever the listening mind puts things it has absorbed. But the larger quality, the sense of a world that has followed its physics all the way to its conclusion, completely and without remainder. That is what carries past the waking mind into whatever quieter state the night produces. A world that is what it is, entirely, without ambiguity, without the provisional quality of a world still in the middle of its story. Venus is in the middle of its story. Every planet is always in the middle of its story. But the chapter it is currently in, the chapter of the thick atmosphere and the sulfuric acid clouds and the retrograde rotation, is a long and stable chapter, and from inside a human lifetime, it looks like an ending even though it is not one. It looks like arrival. And in that arrival, in the dense, hot, completely committed atmosphere of a planet that has been doing this for hundreds of millions of years and will continue for billions more, there is something that functions at the edge of sleep as a kind of anchor, not an invitation to stay awake and think, an invitation to stop. The planet does not need thinking to continue. The clouds do not need observation to circulate. The surface does not need documentation to exist at 465 degrees under its orange light. Venus is entirely self-sufficient in its being. It does not require anything from the sleeping mind. Let it be there. Let the clouds circle without being watched. Let the surface sit in its permanent thermal equilibrium, hotter than any oven, calmer than any place on Earth. Let the Maxwell mantis rise to their 8 kilometers in the dark, coated in their metallic condensates, unchanged from what the Magellan radar showed them to be in 1991. Let the isotopic signature of the vanished ocean persist in the trace water vapor of the upper atmosphere, unread by any instrument tonight, carrying its message about the past into the indefinite future. Let the retrograde rotation carry the hidden sun from west to east in its long, slow arc. Let the super-rotating cloud layer complete another fraction of its 4-day circuit. Let the phosphine, real or not real, biological or abiotic, do whatever it is doing at 55 kilometers altitude in the dim, hazy equatorial zone where temperature and pressure briefly resemble somewhere habitable. Let it all continue without witness. There is a particular kind of attention that the late hours of the night make available, not the focused, directed attention of reading or problem solving, but something softer, a receptive attention, a willingness to hold something without analyzing it, to let a fact be a fact without immediately converting it into implications or comparisons or questions. The surface of Venus is 465 degrees Celsius. Not a warning, not a comparison, not a data point to be filed and retrieved. Just a temperature. Just a number that describes the actual thermal state of an actual place in the actual universe. A place that is, right now, at that temperature. Has been for hundreds of millions of years, will be for hundreds of millions more. The number does not require anything of the listening mind. It simply describes what is. The clouds of Venus are moving at 100 meters per second. Not fast relative to anything human, not slow relative to anything geological, just moving. Continuously, in a loop, 4 days to complete one circuit. The same molecules, sulfuric acid, carbon dioxide, sulfur dioxide, cycling through the same altitudes they have been cycling through for as long as the current atmospheric state has existed. Moving? Always moving. The surface below the clouds is not moving on any scale that matters tonight. It is simply there. The volcanic plains, the tesserae, the Maxwell Montes with their metallic condensates, the coronae marking the positions of ancient mantle plumes, the lava channels that once carried flowing rock for thousands of kilometers across the surface. All of it is there, right now, exactly as it was 1,000,000 years ago, and as it will be 1,000,000 years from now. That kind of permanence, not the permanence of something that never changes, but the permanence of something that changes so slowly that human time cannot register the change, is a particular quality. It belongs to geology, to deep time, to the timescales that operate far below the threshold of anything lived. The planet does not need to be watched to be real. It is real in the same way that everything is real when no one is looking, which is to say, entirely and completely and without any dependence on observation. Venus is out there right now, turning, burning, reflecting, waiting in its geological patience for the instruments that will ask the next questions and receive the next surprising answers. The light from its cloud tops is currently in transit toward Earth. In a few minutes, it will arrive. In the morning, if the sky is clear and the geometry is right, Venus may be visible on the horizon. The morning star, the evening star, the second planet, the twin that isn't, the mirror that shows a different history. Bright, unwavering, entirely itself. If you are still awake to see it, it will be the brightest light that isn't the moon. Steady where the stars around it flicker. That brightness is sulfuric acid clouds reflecting a star. That steadiness is 92 bars of atmosphere, too dense to show atmospheric turbulence from a distance. That light is the end of a chain of events that began 4 billion years ago. And if you are not awake to see it, if the night has done what nights are for and carried the waking mind down into the quieter regions that sleep opens, Venus will still be there, still bright, still steady, still turning backwards in its endless 243-day rotation. It does not need to be seen. It simply is. Everything in this story is real. Venus is out there right now. If this kind of science, told slowly, at the pace the night allows, has given you somewhere to rest tonight, please consider subscribing to Quiet Science at bedtime. A like, a subscribe, a notification turned on. Each of those things helps this channel continue. There are more stories, more planets, more of the science that the daylight hours move too quickly to hold. They will be here when you come back. For now, the night is doing its work. The planet is doing its work. And there is nothing left to do but let both of them continue. Good night.